Hello my dear NEET aspirants and welcome you all to your own platform PW. This is your physics mentor Gaurav Tiwari and today we are going to complete the first chapter of grade 12 NEET Physics, which is electric charges and fields in one shot. I know my dear NEET aspirants that this is a huge chapter, but rest assured I have covered every topic with detailed explanation, and concepts that are difficult to understand are explained with some awesome and easy to understand experiments. So I assure you, if you watch this lecture till the end, you will feel confident about your conceptual understanding of every part of this chapter. And finally, I'll be sharing a free DPP for your practice along with the lecture notes that you can access on the app through the link given in the description. My dear aspirants, PW is the most loved education platform in India, and so many aspirants are already achieving their dreams every year, and that too at the most affordable prices. You can also explore the app through the link given in the description. And now let's start the chapter. Alright dear kids, so the chapter electric charges and field is quite a big chapter, right? So there are so many things going on in this chapter, which is why many kids feel that it is overwhelming, right? It is overwhelming, but here we have divided the chapter in a very structured manner, right? Here you can see that the entire chapter is divided into 4 parts, 1, 2, 3, 4. In the first part, you have these 4 things. We will talk about electric charge, methods of charging, electroscope and Coulomb's law. So this is an easy part. The second one talks about the electric field, field line, properties of field lines, and then electric field of different bodies. Again, slightly technical part. The third part is most technical, right? The third part is, slightly difficult, you will say. It talks about the Gauss's law, it talks about the area vector, it talks about the application of Gauss's law. So it is lot more important. And then the fourth one is talking about the electric dipole, again an easy part. So out of these 4 segments, only the third segment is difficult. And by the end of this lecture, let me assure you that all 4 segments will be crystal clear for you, right? Because in the third one, where the most difficulty lies, I have used so many demonstrations to explain you each and every concept, right? So everything will be very intuitive by the end of this particular lecture. So let us start the first segment of this particular lecture without any delay. Let's have a look at the first topic. So this is the previous year analysis, by the way. If you look at all the segments, this is how many questions were asked in the previous 10 years, right? And this is the first segment. So we'll talk about electric charge and its properties, methods of charging, electroscope and Coulomb's law. It's a small section. We can talk about these things in a very quick manner. So let's get away with them, right? Okay. All right. So here it is. So here you can see that what is charge. So just like a body can have a mass to itself, right? Mass is an intrinsic property. We don't provide it, right? The body simply by existing has it. So just like that, the charge is also an intrinsic property of the body. So there are total 2 intrinsic property. One is mass, one is charge, right? So a charged body exerts a force on other charged bodies that are placed near it, right? And this force could be attraction or repulsion, we know that. And we have a basic idea about that as well, that the like charges will attract or repel. The like charges will repel, unlike charges will attract, right? So we know about that part basically. So here you have the same thing going on. The unlike charges are attracting and the like charges are repelling each other, right? Okay. So here the thing is, how does a charge basically comes into the picture? We have it is ingrained into the atom of every body, that every body has electrons moving around the nucleus, right? And the outermost electron sometimes gets weakly attached to the rest of the body or rest of the atom, right? And that is why they come out in the lattice of the body and they become free electrons, right? So what happens when you have a body like this, all right, and there are so many atoms you can imagine. So the outermost electrons of each atom, they pop out, especially in conductors, right? And they are available to carry the electricity from one end to the other end, right? So these are called as free electrons. They are responsible for carrying the electricity, right? But if you talk about the stationary charges, right, this is for the moving charges. But if you talk about the stationary charges, my dear kids, so what will happen? Then you will say that everything by default is neutral. Everything by default is neutral. That means everything has equal number of electrons and protons. The number of electrons and number of proton in everything is same, right? But what happens, protons are there in the nucleus of the body. You cannot remove them, you cannot add them, right, without applying huge amount of forces, because they are attached with nuclear forces, right? So the number of protons you cannot change easily, right? So when you are carrying out the process of charging or discharging, what is actually changing? The number of electron, right? So any method of charging involves changing the number of electrons in the body, right? Any method of charging involves changing the number of electrons in the body. If the number of electron and proton are same, it is neutral. If electrons are more, it is negatively charged. If protons are more than number of electrons, it is positively charged, right? That's how the charge is created, right? Electrons and protons, they have the same amount of charge, but the opposite nature is there. Electrons are considered to have negative charge, protons are considered to have positive charge. Simple stuff, right? These are all very simple stuff. So nothing very difficult about all these things. So here it is, right? Here it is. So we have electrons and protons going on for each other, right? So right now, what we want to do is we want to measure the charge, right? To measure the charge, what are the things that you can use, right? So we can say that if you ever want to measure the charge of a body, you can say that, let's say this body has 5 electrons and 3 protons. So due to the 5 electrons, it has 5 units of negative charge. Due to the 3 protons, it has 3 units of positive charge. So effectively, it has 2 units of negative charge, right? E stands for a charge on a single electron, which is 1.6 into 10 to the power minus 19, right? So this is what we have over here. Np equals to 3, Ne equals to 1. So it has more proton than electron. So effectively, it has 2 protons extra than an electron. So effectively, it has 3 units of positive and 1 unit of negative. So it has effectively 2 units of positive charge. Very basic stuff, right? So this is what we have over here, right? Okay. Now, let's talk about a property of the charge, which is conservation of charge first of all. So when we talk about conservation of charges, my dear kids, here you can say, in a isolated system. So this system is isolated, right? Right now these two things are separated, right? This charged body has 1, 2, 3, 4, 5 electrons, right? And 1, 2, 3, 3 protons, okay? And the other charged body has 3 protons and only 1 electron, right? Okay. And initially they were separated. Okay, the whole thing is separated from the environment, right? And they are individually separated from each other as well, right? Now what is happening? What is the effective charge in the system? So on the left side, we have 2 units of negative charge because 2 electrons are extra. And on the right side, we have 2 units of positive charge, right? Because we have 2 protons extra, right? Okay, right. So effectively, if you add them up, the net charge before you remove this thing is 0. 2 electrons plus 2 protons, right? The net charge is 0, right? The net charge in this system is 0 in this situation, right? Initially, this is the situation. Now, if you touch them, right? So what will happen? Some of the charges will move from here to here, right? And this is the new situation, right? This is the new situation will be. Now, even after the transfer of charges is happening, my dear kids, even after the transfer of charges is happening, is the total number of charge, is the total amount of charge has changed? We can say no. The total amount of charge has not changed, even if the transfer of charge is happening between them, right? So if I consider this as a system, so the transfer of charge is happening between them, we will say that the total charge is going to remain same. The total charge is still same. Now think about it, even after transfer, think about the total charge right now is still 0, right? Okay, all right. So now you see that there are 2 intrinsic properties in the matter, as I've told you. The first thing is charge, the second thing is mass, right? But the main thing you will say that, the charge has 2 types, positive and negative. Well, while mass do not have negative mass, it's always positive. Charges can attract or repel, right? That's a electrostatic force. While the mass is always attract, gravitational force, right? Okay. Charges are velocity independent. So if there is a charge particle having a charge 1e, it is moving, doesn't matter how fast, it will always have 1e charge on it. But masses are relative, right? The Einstein told that, right? So if the mass is moving, its moving mass will be different than the rest mass. So this is the moving mass, this is the rest mass. It depends on the velocity, right? But that is not meaningful for now, that what will be the moving mass. But the idea is, if the mass is moving, right, at a much, much higher speed, so during the movement part, its mass will be different, right? Now, charges are always conserved and mass can be converted into energy, right? This is the thing, right? Charge cannot exist without mass. It is true, charge cannot exist without mass. There is no massless object that has charge on itself. While mass can exist with zero net charge. Of course, there are so many neutral things around us, right? Zero net charge, okay? Now, the dimensional analysis you can do. Q equals to IT. What will be the dimension of the charge? So, dimension of a current is ampere, dimension of time is seconds. So, you just put A and T, right? Dimension of current is ampere, right? In some books, current can be written in this dimension. In some other books, you can use the dimension I for that. So, IT or IA, whatever you can say, is the dimension for the charge, right? Now, how can you charge a body, right? These are easy parts. So, first of all, let's get them off very quickly, right? So, we can have negatively charged body, neutral body, positively charged body. So, negatively charged body doesn't mean that it only has negative charges, right? As I have already told you, charging and discharging only happens through changing the number of electrons, right? Protons you cannot change, right? This body is negatively charged. Why? Because it has more electrons than the number of protons. This is neutral because it has same number of electrons and protons. And the last one, it has less number of electrons than the protons, so it is positively charged, right? Okay. Now, you know the material type, it's conductor and insulators, right? It's very easy part, so we will do that part also very, very quickly. Then we will move on to the Coulomb's law, right? These things are there in the syllabus, that is why we have to cover them up, right? Very easy. I know that most of you kids know that, but as soon as we jump onto the Coulomb's law, things will start getting better, right? So you see that we have the conductors with us. So right now you see that we talk about the gold or the steel. These are all the conductors. Why are these things called conductors? Because they have free electrons, right? They have free electrons. So energy, if it is entering on one end, let's say the heat energy or the electrical energy, it can travel through them, right? So the same thing is happening, right? Energy can flow freely because it has lots of free electrons. What happens with the wood and rubber, right? These are insulators and the energy cannot travel through them, right? Okay. So charging of conductors, this is the conductor we have. How can you charge a conductor? So you see that there are three ways you can use to charge a conductor, right? There are three ways you can use to charge a conductor. The first method is charging by conduction, right? First method of charging is charging by conduction. So in this one, body that is charged and there is another body that is uncharged, right? We have to put them in physical contact, either touch them or touch them with the help of a wire, right? So through the conduction, charging can only happen when there is a physical contact, right? So right now what is happening? So there is no physical contact, no charges will move, but as soon as there is a physical contact, what will happen? Charges will move from the charged body to the uncharged body, right? So this is what is going to happen, right? Okay. So now what is happening over here, right? Charging by induction, on the other hand, it does not involve a physical contact between the bodies like this. You see that? This is the charged rod. It has positive charges on it. Initially, when you have a ball that is uncharged, right? So it has positive and negative distributed like this, right? So what will happen when you take a positively charged rod near it? What will happen? The negative charges will be pushed on the other end, right? So on the other is the negative charges, sorry, will be attracted towards this one, and the positive charges, because it's a positive rod now, so positive will be pushed because of that, right? So what will happen? After some time, you will find that one end is becoming positive and the other end becomes negative because this positive rod attracts it. This positive rod attracts the negative electrons toward itself, right? So this is what is happening over here in this situation. So right now what is happening? Charging by induction. Charging by induction, you have seen it, right? You see that right now what is happening? So initially this was the situation, and when you put the rod right next to it, right? This rod is positively charged. So you see that electrons have moved from this place to this place, or electrons were initially randomly distributed and now they are moving closer to this particular part, right? So that the concentration of electrons gets higher in this side. Okay. Now what is happening? Right. The other end can be grounded, and in that way this side of the charges will be grounded and the negative are locked with the presence of the positive charge, right? So you know that even if that is removed and the other part is grounded now, so the negative, and you remove the ground as well, so what will happen? The negative charges can be redistributed. That's one trick to produce a permanent charge through induction, by grounding that thing, and then after the positive charges have been grounded, then you can remove the positively charged source and then distribution of the negative charges will happen, right? So this is what we have seen, right? Now, insulators, you cannot charge insulators by conductions, right? Okay. Now, the last method of charging is called as charging due to friction. Last method of charging is called as charging due to friction. So what happens? When two bodies are rubbed against each other, electrons get transferred from one body to another body. So which body is going to transfer the electron and which body is going to accept the electron? Very quickly we understand that. Let's say we are rubbing two bodies, body number 1 and this is body number 2, right? So it depends on the electronegativity of those two bodies, right? The one which has more electronegativity will accept the electron, and the one that has less electronegativity will lose the electron. I believe the idea is very, very clear, right? So here we have it, charging by friction going on. So we have a silk and glass. So one of them is more electronegative. So when you rub them, what happens? Since the silk is more electronegative, so it keeps the electron with itself, right, after rubbing, and the glass loses the electron, right? Okay, so that was the basic part and we are done with that basic part, right? Most kids are very well aware of that, but it was a part of the syllabus. This is why we have to cover it. Now, here we have it, the Coulomb's law, right? Again, a very simple concept. You just have to know about the Coulomb's law and its vector format, right? Then the life is going to be very easy on you, right? Most critical concepts are there in this chapter, like Gauss's law is there, and concept of area vector is there, the concept of electric field is there, a little bit of calculus is also there. So all of that we have talked in a very detailed fashion, right? So here we have Coulomb's law. So what is happening in the Coulomb's law? Now we have figured out that two charged particles that are interacting with each other, the interaction between them is not entirely random, right? So if the charged particles are like this one is Q1 and this one is Q2, and they are separated by a distance r. So if you move them apart, the force between them reduces dramatically. And with the help of multiple experiments, we found that the force between them changes with the square of distance between them, right? The force reduces with the square of distance between them, right? And now, if you increase the value of charge on them, right? If you double this and double this, the value of force will also increase. If you triple this and if you triple this, the value of force increases, right? So what happens? The value of force acting between the charges increases if the magnitude of charge increases, right? So we found that the value of force increases if Q1, Q2 is increasing, right? This one, let's say, is Q1, the other one is Q2. So the force increases with the product of Q1, Q2. If you join them, so F is proportional to Q1, Q2 by R square. And here a proportionality constant will come up when you will remove the proportionality sign. That constant is 1 upon 4 pi epsilon naught. When you are talking about there is air or vacuum between the charged particles, then you can use this proportionality constant. If there is any other medium between the charged particle, you have to use another proportionality constant, right? 1 upon 4 pi epsilon naught is also called as K. So just to simplify the equation, it will look like this. F is K Q1 Q2 by R square. Very simple observation. This is what you are going to get, right? Okay. Now let's talk about this next part. So here what is happening, right? Coulomb's law in the vector format. So how will, because it's representing the force between two charged particles, right? So you can also represent this thing in a vector format as well, right? So what will be the vector format of Coulomb's law? Again, there are two charged particles like this, right? The first one has a position vector r1, the second one has a position vector r2, right? The force on this one is in this direction, let's say one is positive and the other one is negative. So the force on this one is in this way. So force on first due to second, F12, and force on 2 due to 1 is F21 in this way, right? Okay. Now I want to write down the value of this force in a vector format. So how will I do that? If any vector is there, let's call this vector as A vector, and the direction in the unit vector in this direction is A cap, right? And the magnitude of this vector is, let's say, only A. Magnitude of A vector is only A, right? So how can I write this vector in a vector format? So A vector is magnitude of A vector into unit vector in the direction. That's how you write any vector in the vector format, right? So if you want to write the force in the vector format, how can you do that? Magnitude of force, which is K Q1 Q2 by R square, into the unit vector in this direction. So what will be the unit vector in this direction? Right. Unit vector in any direction is, unit vector in the direction is complete vector upon the magnitude of that vector. Got it? The unit vector is complete vector upon the magnitude of that vector, right? So this is what we have to talk about, right? So let's try and do that, right? So this is the magnitude of force between the two charges Q1 and Q2 without any problem. We know that, right? Now, if I multiply this force with a unit vector in the direction, I can get the force in a vector format, right? This is absolutely correct. Now, if I want to write down the value of this unit vector, so unit vector is vector upon its magnitude, right? So just put the value, right? R21 upon the magnitude. So magnitude of the distance vector is R only, right? The magnitude is only R, right? So R21 is full vector, R21 vector, right? You look at the sign, it is cap, and here it is vector, right? So R21 vector upon R vector, right? And just put the value. R21 vector will be R2 minus R1. R21 vector will be R2 minus R1. So just put it, and this is how you will get it, right? So this is the force in the vector format, right? So I believe the idea is very, very clear. Okay. And now you can say that force on first due to second in this way and force on 2 due to first in this way, they are acting opposite to each other. They are acting opposite to each other. I believe the idea is very, very clear. Look at this particular question, my dear kids. Okay. 2-point charges A and B having charges plus Q minus Q respectively are placed at a certain distance apart and force acting between them is F. If 25% of the charge of A is transferred to B, then what will be the force? Then the force between the charges becomes what? Okay. So we have 2-point charges A and B. We have 2-point charges A and B. Okay. They had the charge Q and minus Q. So they are attracting each other. Right. And now what is happening? The force by which they are attracting each other was F. Okay. If 25% of the charge of A is transferred to B, right? So 25% of this charge is transferred. So remaining charge on this one remain 3/4 of the initial value, right? Q by 4 is given to this one, but it is given plus Q by 4. It's a positive charge, no? So plus Q by 4 is added to this one. So it is minus Q plus 1 by 4 Q. So effectively it is minus 3 by 4 Q. All right. So now the new force will be, let's say, F dash, right? So what will be the value of F dash? F dash will be K times Q1 Q2. So 3 by 4 Q and 3 by 4 Q over R square. Distance has not been changed. Initially the value of force was F, right? Initially the value of force was F. What is that? K times Q1 Q2 by R square. So Q1 Q2 is cancelled out. R square is cancelled out. K is also cancelled out. So we have F dash upon F. It is 3 by 4, 3 by 4. It is 9 by 16. All right. 9 by 16. And this is going to be the value. 9 by 16 is going to be the value, right? So F dash, if you have to find out, F dash will be 9 by 16 times of the original value, right? And it is, of course, obvious as well. So the charges are reduced, so the force should also get reduced. So 9 by 16 is D is the correct option, right? So here we have the permittivity of free space. Now what happens? Whenever we have electric field going on, in a certain space, what happens? The particles of the medium gets polarizes, right? And there is a term associated with that is called permittivity, right? So permittivity helps us understand a particular medium, how is that medium going to interact with the available electric field, all right? Okay. So the value of force is k q1 q2 by r square. You said you already know that. And the value of k is 1 upon 4 pi epsilon naught. This epsilon naught is actually the permittivity of the medium, which is air. Epsilon naught is permittivity of air or vacuum, right? Permittivity of air or vacuum. All right. Okay. Now, here it is, right? So it is k q1 by r square. Now, if it was a medium between them, instead of air, if there is a medium in between the positive and negative charges, then the value of k will be 1 upon 4 pi em, right? Epsilon m, that is permittivity of the medium itself, right? So permittivity of the medium, how will you know that? Permittivity of the medium is relative permittivity into epsilon naught, right? Relative permittivity up into epsilon naught, relative permittivity into epsilon naught, right? Okay, so if for a medium, let's say relative permittivity is, let's say 80, okay, and so it is for that medium, the permittivity of that particular medium is 80 times permittivity of you can say air or vacuum, right? Okay, so this is it, right? So I believe the idea is very, very clear. So now you know that if I have a medium in between the charge particles, right? Let's say this is one charge, this is another charge, and I have a medium in between them, then the new force is 1 upon 4 pi epsilon of that medium, right? Into q1 q2 by r square, right? This is the value of new force, okay? Medium's permittivity is epsilon naught into ER, right? So 1 upon 4 pi epsilon naught into ER q1 q2 by r square, all right? 1 upon 4 pi epsilon naught q1 q2 by r square, that was the original force, or you can say F naught, when there was air between them upon ER, right? So the value of force when there is a medium of relative permittivity ER is there in between the charge particle is 1 upon permittivity of that relative permittivity of the medium times F naught, right? Now, in some books, they are using the notation as K, right? Relative permittivity they are calling as K. But in the beginning, we have assigned 1 upon 4 pi epsilon naught as K. So we will avoid it for now, right? We will avoid it for now. But for going forward, if we are using it in place of ER, we can use, let's say, capital K, right? So that is all. That should not be a big problem, right? It should not be a big problem. A permittivity, just the notation sometimes is different, right? So relative permittivity is there, right? So here you see that when an air is replaced by a dielectric medium of force constant K, right? This force constant K, this is the relative permittivity they are giving, ER, right? The maximum force of attraction between the charges separated by the distance will become how many times, right? You know that the force when there is a medium is 1 upon K times force in the air, right? 1 upon K times force in the air. So I believe the idea is very, very clear, right? So yeah, so it becomes 1 upon K times, right? Now there are certain limitations of the Coulomb's law as well, my dear kids. What are the limitations of the Coulomb's law? First is, it is difficult to apply Coulomb's law when the charges are in the arbitrary shape, because you have assumed that the charges are of point shape, right? You are talking about the charges are point charges. That's why you are measuring the distances and all, and then calculating the value of forces. If the charges have the arbitrary shape, then the application of Coulomb's law becomes very difficult. So it is not valid for charges in motion. It is valid for electrostatics, because when the charges are stationary, then only there is electric field around those charges, right? If the charges start moving with a constant velocity, then there is electric field and magnetic field around them. If the charges are accelerating, then electric field and magnetic field are there around them, as well as they radiate away the energy in the form of electromagnetic radiation, right? So this is the difference. Coulomb's law is applicable in the first case only when the charges are stationary and there is only electric field around them, right? Now the charges must be point charges, as I've already told you. If the charges are way too big, then taking the distance will not be very easy for them, right? Separation must be greater than the nuclear size, of course. Separation must be greater than the nuclear size, because when the separation is too little, electrostatic forces are surpassed by the nuclear forces, basically, right? So right now what will happen, if the distance is reduced by the nuclear distances, so the nuclear forces start coming into the picture, which are huge as compared to the electric forces, right? All right. At last, we have principle of superposition. Principle of superposition tells us a single charge particle will apply certain force on another charge particle. With the help of Coulomb's law, we can understand that. A bunch of charge particle can also apply the force on this charge particle, because electrostatic force is a central force. It acts between center to center like this. Imagine it's a positive charge. It is also a positive charge. So this Q1 will feel repelled by it, right? Like this, right? Let's say this is positive, this is also positive. So due to this one, it is also repelled, and also due to this one, and also due to this one, right? So all I have to do is just add all forces vectorially to get the value of net force on this one, right? So whenever a charge is under the influence of multiple charges, I can get the value of forces applied by all of them and add them vectorially, right? That will give me the meaning principle of superposition, right? That will give me the principle of superposition. You see that this charge particle is experiencing the force due to all of them. So this is why the net force will be vector summation of all of them, right? This is why the vector summation, net force will be the vector summation of all of them. This is what we are going to get. I hope the idea is very, very clear. The question is this: three identical charge particles A, B, and C with the charges plus Q are present on the vertices of an equilateral triangle. Having the sides of A as shown in the figure, find the resultant force on the particle C. We have to talk about the resultant force on the particle C. So what will happen? We have two charges applying the force on this one. Positive and positive will repel. Positive and positive will repel, right? So let's call this is the first charge applying the force F1. This is the second charge applying the force F2. So the angle between them here is 60, so this will also be 60. So the net force will be under root F1 square plus F2 square plus 2F1 F2 cos 60, right? That is going to be the truth, right? So this square plus this square, 2F1 F2 cos 60. Just put the values, right? F1 and F2 both are going to be KQ by R square, KQ by A square, and KQ by A square, KQ by A square, right? Q1, Q2 by R square, no? So F1 is K Q1, Q2 by R square. F2 is K Q1, Q2 by R square. I believe the idea is very, very clear. So now you know the value of F1 and F2 both, and you can proceed with it, okay? So that's pretty much everything, right, about the first section, right? With the first section was fairly easy, and I know that most of the kids are not confused in the first section itself. The confusion will start from the third section, where we are going to talk about the Gauss's law and all. So any section where you find the confusion, you can directly scroll to that particular part, right? And then cover that part, right? Wherever you find the difficulty is there. But I will suggest you to watch this lecture from one end to the other end, so that whatever part is easy, I'll increase the speed so that you can quickly revise it. And whatever part is difficult, I will slow down. I will show the demonstrations, I will show the numerical and everything else, so that that part can be understood really well, right? And if any part is relevant, more important for the NEET exam, conceptually, that also I will explain in a much detailed manner, right? And one more thing, my dear kids, from this particular chapter, I have observed that they are not only asking the numerical problems, they are also asking the conceptual problems, right? So any kid who is absolutely clear with the concepts can ace on those fronts, right? So let's move ahead with the second part, okay? All right, so now let us start understanding the second set of concepts, which is the electric field, right? So here we have the electric field line, and then electric field due to the different shapes, right? So this is what we are interested in. So very easy concept to understand. Here you see that we have two charged particles here, positive and negative. And you see that Faraday wanted to represent how the field around them looks like. So he used a set of lines to represent the field around them. They called it field lines, right? So the positive charge, for a positive charge, they emerge out of the positive charge like this, right? the field lines are outwards from the positive charge and they seem to be terminating into the negative charge like this, right? Like this, right? So this is how it will look like in the case of a charged particle, right? Now you have this thing going on for you, right? So in the case of a positive and negative charge, it's a dipole thing going on, right? So this is how the electric field will look like. It will start at positive and it will end at negative. Look at this line. It is starting at positive and terminating at negative. It is not coming back. So definitely electric field lines do not form a closed curve, do not form a closed loop, right? Look into this situation. Many times in the upcoming part, when we'll understand superposition and all those things, we will talk about the concept of test charge. We will need it. So what is test charge? Test charge is a charge of, it's a positive charge, we will say, right? And it has a negligible magnitude. Why do we consider a negligible magnitude? Because think about it. If you have a positive charge and you place a positive charge right next to it, they will repel. A negative charge, they will attract, right? So if a charge is placed right next to a available charge, it will affect and it will interact with it, right? It will affect the electric field around it, right? Here you have seen it. When you place another charge particle, the electric field in this region changes, right? Now, if I have a test charge, so the property of the test charge is such that it does not affect the electric field around itself, right? So the electric field around itself is not affected with the help of this particular thing. So test charge is a positive charge of very small magnitude which gives the direction and the strength of the electric field at the space without influencing the electric field at that place, right? So the main purpose of the electric test charge is to help us understand the strength of field over here, right? And the property of the test charge is it does not affect the electric field around itself. It's a very small magnitude charge that we assume, right? Okay. So if you want to find out the direction of electric field anywhere in the space, test charge will help you. Let's say that how? Imagine that it's a positive charge over here, another positive charge is negative charge is over here, let's say, right? And I want to know what will be the direction of electric field at the point P, right? How can I know that? Should I guess? No. So I'll just assume a test charge is placed over here at point P. Wherever you want to find the direction of the field, you place a test charge, right? And this positive will repel the positive test charge, like, right? So like this, right? And negative will attract the test charge like this, right? So you see that this is creating the electric field E1 over here. This is creating the electric field E2 over here. And now we can calculate the net electric field over here, right? As a combination of E1 and E2, as a vector summation of E1 and E2, right? So we can easily calculate the value of electric field over here, right? So the thing is requirement of test charge. So how do you calculate the test charge? We have understood what is the meaning of test charge. We have understood, and what is the property of test charge. We have understood. So you see that if there was a body, a conducting body, and you place a charged object, let's say if you place a charged box or a scale right next to it. So let's say that it's a positive charge box or positive charge body. So it will attract the negative charges. It will be inducing itself. So right now what will happen is this side will become negative, this side will become positive, right? So if it was a charged body, you keep it closer to this, the thing. So what will happen? There will be a charge redistribution and they will be charging by induction, right? But if I use a test charge near to this body, I will not be inducing any charge in that case. So the test charge does not induces anything, right? Okay. So here we have it, intensity of electric field. So right now, what are we trying to do? We want to know the intensity of electric field over here at a certain point P, which is closer to a available charge, point charge, right? So we have a point charge and the distance r away from the point charge, we have a point P. We want to know that what is the intensity of field at the point P, right? Listen it again. We have a charge Q, point charge Q. And at a distance r away from the point charge Q, we want to know the value of electric field. How will you do that, my dear kids? We can say, this is the positive charge, right? Wherever you want to know the value of electric field strength, I will assume a positive test charge over there. So you will have a test charge at the point P. This is the test charge you have assumed, right? Now, this is positive, so this will repel and this will be the direction of electric field, okay? All right. So what is the intensity of electric field over here? intensity of electric field is the force experienced at that place by a unit charge, right? So let's say the charge placed over here is Q naught, right? So the force experienced by unit charge, F upon Q naught, because the value of the charge is Q naught. So force per unit charge is F upon Q naught, right? If the force was, let's say this charge was, let's say 10 Coulomb, so it will be F upon 10 Coulomb, right? So whatever force is experienced by unit charge at that place will become the electric field intensity at that place, right? So here you can see that electric field intensity is force per unit charge, which is Q naught. So F is E into Q naught. And here we can say that intensity of field will come out like this. So value of force you can calculate with the help of Coulomb's law. K times Q1 Q2 by R square. So Q and Q naught upon R square. Just put the value over here. Q naught and Q naught will cancel out. So the value of electric field intensity at a distance R away from the point charge Q is KQ by R square. The value of electric field intensity at a distance R away from a point charge Q is KQ by R square. I believe the idea is very, very clear, right? Now, here we have it. What kind of variation do we get from this place? So we can say that the variation is following the inverse square law, right? So inverse square law, variation is following the inverse square law, right? So right now you can say that if you move away from this thing, so it will move like this, right? Inverse square law. Intensity of field varies with inverse square law with the distance, as you can say, right? Now you have the intensity of electric field in this situation going on when you have a negative charge. So again, the direction of field will change only and the value will remain same, right? Because the charge is still Q. So KQ by R square, but the direction is this way. And how do you know the direction of field? By assuming a test charge at that place, and you see that it is attracted at the particular part, right? So here it is. Okay. Now, if you want to know the value of electric field intensity in a vector format, because again, it's a vector quantity, right? So you can just multiply this thing with a unit vector in this direction. So what is the unit vector? For complete vector upon R. Unit vector along this way is complete vector upon the magnitude of this thing. So it is going to be KQ upon R cube into R cap, right? So what is the dimension of this particular thing? What's the unit of this particular thing? Just put the value of force and value of, unit of charge. That will give you the value of electric field intensity, that is Newton per Coulomb. And you can also calculate the dimensional formula, which is this, right? Now, here we have the principle of superposition, very useful, right? It is useful till the end of the chapter itself, right? You see that? Principle of superposition helps us figure out the effect of a charge distribution, right? Here you have Q1, Q2, Q3, Qn, and so on. And you have a point P where you want to calculate the net field due to all the point charges. Through one point charge, you can say it is KQ by R square at a distance R. Through all the point charges, how will you calculate? So my dear kids, first of all, you will assume a test charge over here, and it will be better if you assume a unit positive test charge, right? So what will happen? Q1 and this one, let's say that this is positive, all of them let's say are positive, right? So Q1 and this one is going to repel. Q2 and this thing will repel, right? Q3 and this thing will repel, and Qn and so on will also repel like this. So by adding all these electric field intensities, you can get the net value of electric field intensity at point P. So if it is E1, E2, E3, E4, En, just add them vectorially to get the value of electric field intensity at the point P. So here you can see that with the help of this unit charge, you can, with the help of the test charge, you can say, get the value of net field intensity over here, right? So you see that, that's what we are doing, adding all of them vectorially, right? So net field intensity is vector summation of electric field intensity due to all the individual charges, right? Now you have a regular polygon arrangement. This is a very, very interesting case, right? So here what is happening? The net field due to all the available charges again will be summation of all of them, right? But my dear kids, you see that here, imagine we have a positive charge like this and a positive charge like this, right? And over here at the center, you want to know the net field. So here you will assume a unit positive test charge or any test charge Q naught, right? So this charge positive, let's say this is Q and this is Q as well, right? So what will happen? This one will repel it and this one will also repel it, right? Since Q and Q are same and this is the middle point, so this distance and this distance will also be same, right? So the value of KQ by R square and KQ by R square will also be same. KQ by R square, Q is same, R is same. Both of these intensities are same. So they are cancelling out vectorially. So the net electric field intensity over here will be 0, right? Look into this situation. Think about this charge and the charge diagonally opposite to that, right? They will cancel out each other. Similarly, this one and this one is cancelling out each other, right? So if you have this kind of symmetric arrangement of charges, they cancel out the net electric field at the center of that geometry, symmetric distribution, right? This is a symmetric distribution of charges. How will you know that if the charge distribution is symmetric or not? How will you know that? My dear kids, the best way to know that if the charge distribution is symmetric and it will cancel out all the electric field at the center or not, right? All the charges must be the same, right? And it can only happen when just try to rotate the entire geometry by a certain angle. How much is that angle? We can say that 2 pi by number of sides, or you can say number of charges, whatever. So right now you have how many sides in the polygon? You have, this is octagon, right? 1, 2, 3, 4, 5, 6, 7, 8, right? So so these are, it's octagon. So divide 360 by 8, right? And rotate that value, rotate it by that value, right? So I believe the idea is very, very clear, right? For example, think about it. If this triangle is there, right? And how will you know that if at the center of this triangle, all the electric field will cancel out or not? So all the charges are same, Q, Q and Q. So think about it. If you take 2 pi by the number of sides or the number of charges, which is 3. So it is 360 by 3, it is 120, right? So is it symmetric or not? Try to rotate it by 120 degrees, right? So rotate it by 120 degrees. So what will happen? You will find that we again get the similar distribution of charges. The distribution of charges is not affected at all, right? The distribution of charges is not affected at all. Just rotate the entire geometry by 120 degrees. So it will not be affected, affecting anything at all. Right, so what will happen? In that situation, you can say at the center, the net electric field will cancel out each other. So due to this one, field is here, due to this one, field is here, due to this one, the field is here, and all of them will balance out. So the net field at the center will become 0, right? Similarly, in this arrangement, all charges are same. It's a square, right? And you see that the net number of charges is 4, so 360 by 4 is 90. If you rotate it by 90 degree, again, it will remain the same distribution. So you see that if the charge distribution remains unaffected, it's a similar distribution of charge. So at the center, the net field is going to be 0. So wherever you going to get, let's say, a symmetric distribution of charge, that will give you one thing, and that one thing is the net field at the center is going to be 0, right? For this pentagon, again, 360 by 5, it is 72, right? And if you rotate it by 72 degrees, again, the structure will not change. Thus, it will still remain symmetric only. So you see that the net field at the center will be 0, right? So over here, you see that two identical charge particles, A and B, are there. Identical charge particles are there, A and B. There are only 2 charge particles, not 3. There are only 2 charge particles. Each of them are Q, plus Q. And they are on the vertices of equilateral triangle, okay? So they are on the vertices of an equilateral triangle of side A, okay? So the side length is A, okay? All right. Find the magnitude of resultant electric field at the point C. So at point C, we need to find out the net electric field. We can do that easily. How? You see that, imagine a unit charge over here. So positive is going to repel that positive, right? This is how it will give. And this positive will also repel this positive. So this is how this will give, right? Now, since this angle is 60, this is also going to be 60 degree only, right? So you know that this is the, let's say, this is the charge number 1. This is the charge number 2. So charge 1 is creating the electric field E1. And the charge 2 is creating the electric field E2, right? Now you see that since the value of charge Q is same and the distance, this distance and this distance is same, A. So KQ by A square and KQ by A square will be the magnitude of electric field. We will say that the magnitude of electric field E1 and magnitude of electric field produced by the second charge is same, which is kq by a square, right? Okay. Let's call this thing as equal to E. Okay. Right. Now, what will be the net field? Because we have to find the magnitude of the net field over here. So just find the resultant. We know that the resultant of these two things, or you can say the net electric field, is going to be under root p square plus q square, which is E1 square plus E2 square plus 2E1 E2 cos theta, right? So under root E1 square, which is E square plus E square plus 2EE cos 60. All right. So it is 2E square, 3 square cos 60 is 1 by 2. So it will become 3E square. So it will become E root 3. So what is E? E is kq square, kq by a square. So it is kq by a square root 3. So that will give you the value of electric field over here. Root 3 kq by a. So this a square will be there, right? So root 3 kq by a square. So option A is correct, right? Root 3 kq by a square. Option A is correct. I believe the idea is very, very clear. Let's move on and talk about the next idea. So here we have to analyze the electric field in this particular situation, right? And we are talking about a concept called as neutral point, right? Or equilibrium point, you can also call it. So where is the neutral point when you have two equal charges? Think about it. I have a positive charge here and I have a positive charge over here, right? Imagine I want to find out, is there any point on the axis of this charge distribution where I get zero electric field? So see that, right? I have this line going on for me, right? And you see, what am I doing? Basically, I have assumed a test charge over here, Q naught. This positive one is going to repel it. This positive one is going to repel it, right? And they are trying to oppose each other. So definitely, there will be a place somewhere where they will oppose each other just enough when they can cancel out, right? It is not necessary that they are same, but they are identical. That means they are like charges, I would say. They are like charges, not identical charges. They are like charges. That means if it is positive, the other has to be positive. If it is negative, the other has to be negative, right? In case of like charges, they can have different magnitudes, Q1 and Q2. This could be a 2 Coulomb charge, this could be a 8 Coulomb charge, right? So, but they are positive. So we can say if we have like charges of same kind, then there is a place, there has to be a place in between them where the electric field due to both of them cancels out, right? And that place, let's say, is A, right? And it will be called as neutral point. What do you call it? Neutral point. I believe the idea is very, very clear. All right. And now how to calculate the place of this neutral point? Just think about it. Imagine a unit charge over here. Calculate the value of electric field over here and calculate the value of electric field over here, right? Because the net field has to be 0. So the electric field created by both of them has to be equal, right? Just equate them and get the value of them, right? So let's try and calculate it. Where will I get the neutral point in the case of like charges? This is the first thing we want to understand. Where will I get the neutral point in the case of like charges? So let me rub this thing. Right. Where will I get the neutral point in the case of like charges? And the same thing, where will I get the neutral point in the case of unlike charges, positive and negative? So I have a negative charge, I have a negative charge, like charges. I have a positive charge, I have a positive charge, like charges. Now, in between them, if I place a test charge, so I produce the electric field in the opposite directions. Clearly, this negative is going to attract it, and this negative is going to attract the positive test charge. So they will be opposite in, the electric field will be opposite. So there is a possibility of them cancelling out in between them. Same goes for this positive and positive. I can assume a positive charge test charge between them. So this positive is going to repel it. This positive is going to repel in this way. So there is a possibility that between these two charges, that I have some place where the net electric field get cancelled out. right? But what about if I go beyond that, right? If I go beyond that, then what will happen? At this place, you see, over here, the electric field by this one, it's a positive test charge. So electric field by this one is in this direction, it is attracted. And the other one is also attracting it. So it will never cancel out beyond that, right? And similarly, if you go beyond in this region, so both of them are attracting in this way. Same goes on for the positive charges as well. So beyond the charges, there is no place where you can get a neutral point. In between the like charges, you will find somewhere, you will find at least one place where you'll get the neutral point. I believe the idea is very, very clear. Now let's calculate what is the location of neutral point. Let's say that over here you get the neutral point, which is at a distance x from the first charge. The total distance between the charges is L, so the remaining will be L minus x. So from this one, it will be kq1 by x square. From this one, it is kq2 by L minus x square. Just equate them because the net field has to be same, right? They has to be equal. That's why we have a neutral point over here. So just equate them, right? E1 and E2 should be same. And once you do that and solve it, get the value of x to be this. Get the value of x to be this. So under root q1 upon root q1 plus root q2. Under root q1 upon root q1 plus root q2, right? Okay. So here we have x that is measured from the from the charge q1, right? X is measured from the charge q1 over here, right? Now think about it. If to get the neutral point, I have to get closer to the charge q1. Think about it, right? And even if the let's say this point P is a neutral point, this point P is much further away from the second charge. Still, it is producing enough field to cancel out the field produced by this one. So clearly this charge is bigger, that is why it is capable of producing enough field at a much larger distance, right? And this charge has to be smaller, right? So by simple observation, we can say Q1 is a smaller charge over here and Q2 is a bigger charge over here, right? So the way to remember this formula will become x is under root a smaller charge upon under root one charge plus under root second charge into the total distance between the charges. So this formula will help you to figure out the distance of x, which is distance of neutral point from the smaller charge, right? Distance of neutral point from the smaller charge. I believe the idea is very, very clear. Let's move on and talk about the other possibility where here it is, x is calculated, we have this part, right? If q1 and q2 are same, then where will be the neutral point? So if q1 and q2 are same, just put q1 and q2 equals to q, so you will get at L by 2. So in between, exactly at the middle point, you will get the neutral point. Here, the second possibility, if the charges are unlike, one is positive and one is negative, then where will you get the neutral point? You see that it is positive, the other one is negative, right? Now, in the region between these two charges, you see, imagine a unit test charge. So this positive is going to repel it, this negative is going to attract it. So both of them will add up, right? So in the region between these two charges, there is no place where the net field is cancelled out, right? So we can say if the charges are unlike, if the charges have different nature, then there will be no place in between them where we will have neutral point. But if I try and jump outside, you see that over here, the positive is going to, this is a test charge, the positive is going to repel it and that negative is going to attract it and they must cancel out. And same goes on for this particular situation, right? Over here as well, right? So right now, try and understand that, let's say you can get the value, let's say this distance is x, the total distance is L, so the distance from the second one will be L plus x, right? So electric field due to first one, electric field due to second one, you just have to equate them and get the value of x again, right? So you see that. So we are assuming that it is at a distance x from the neutral point here is at a distance x from the first charge, right? The total distance between the charges was L. So distance from the second charge will be L plus x. So for the neutral point, E1 and E2 must be same. So E1 is kq by x square and E2 is kq by kq2 by L plus x whole square, right? Just solve it and get the value of x to be this. Under root q1 upon root q2 minus root q1, right? Under root q1 upon root q2 minus root q1. So you see that x is measured from this charge, right? And again, with the common sense, you can say, since we are getting the neutral point much closer to the charge q1 and the charge which is much further away is able to cancel this cancel the first field out. You see that this is producing positive charge. It's a positive test charge. So E1 is produced by this one, right? So the electric field of first one, which is much closer, is cancelled out by E2, which is produced by this one, right? Which is much further away. So this has to be bigger charge. This has to be the smaller charge. So one good way to remember this formula would be x is the distance from the smaller charge for the neutral point is under root q1 upon root q2 minus root q1 into L, which is the distance between them. Here it is minus. In the previous formula, it was plus, right? Root q1 plus root q2, right? All right, so let's have a look at this question. So here we have a 2 Coulomb charge and a minus 8 Coulomb charge. It's a unlike pair of charges, right? And we have to find where are we going to get the neutral point. So the answer would be very clear. We cannot get neutral point in this place because as you know that if I assume a unit test charge, the positive will repel it, negative will attract it. So they are not, there is no place where they will cancel. Everywhere they are adding up in the same direction. So here you will not get the neutral point. Towards the larger charge, if you place it, place a test charge, negative will attract it, and the positive charge, the smaller one, is much further away and it is also smaller. So it will create a little repulsion. So basically there will be no place where the repulsive force is enough, the electric field here towards this side is enough to cancel out this one, right? So in this region again, there is no place where you can get the neutral point, right? So in the case of unlike charges, you can only have the neutral point towards a smaller charge, right? So let's say that over here you get the neutral point at the point P, and that point P is at a distance x away from that smaller charge, right? So what would be the value of that? X would be under root of a smaller charge, which is 2 Coulomb, upon under root of bigger charge minus under root of a smaller charge into the distance between them, which is, let's say the distance between them is given as 9 meters, right? So just multiply that by 9 meters, okay? And just solve it, right? So this will be the value of x, right? I hope the idea is very, very clear, right? So let's move on and talk about the next idea, right? The EX curve, let's have a look at that. It is also very, very important. So here we have it. So for when we are going to draw the EX curve, right, how the electric field is going to vary near a charge distribution. So if you have a single charge, you know that the electric field will move like this, right? E is inversely related to the square of R, inverse, square relation. So this is the kind of distribution you will have around a positive charge, right? If you have a negative charge, so the negative charge will, have electric field lines like this, right? So positive charge have electric field line like this, right? So you see that this is X and this is electric field, right? So now this is X and this is electric field, right? So you see that here, if you are representing the electric field towards right as positive, you have to represent electric field towards left as negative. So how will you show this side? So when you are moving towards right, the electric field is reducing, right? But it is in the negative side. So electric field will not be in the upper part, right? Over here it is positive and over here the electric field is negative. And towards left, electric field has to be negative. So it will go in this way, right? So it is closer, and when you move further away, it reduces. So I can draw it better, right? Just like this. I believe the idea is very, very clear. So just try and understand this part as well. So here we have it. A positive charge is there. So this is the EX curve of the positive charge, right? So when you move further away, so you move in this direction. So you see that electric field varies with this, right? And when you move this way, when you move towards negative axis, negative x-axis, so x-axis is also negative, right? Okay, and what will happen? Electric field is in this way, right? So electric field is in this way. This side electric field is positive. The other side of the electric field has to be negative. So it will move below the axis, right? So just like that. So this is how it will look like, right? This is how it will look like. So I believe the idea is very, very clear in this situation, right? So now this is the EX curve for this small negative charge. So what is happening, right? Here we have it. The electric field lines are like this, right? So electric field lines are like this, right? So over here and over here, electric field lines are like this, right? So how will you do that? When you move in the positive direction of X, right? When you move in this way, the electric field is in this way, right? So when the electric field is towards this way, which is the negative side of the electric field. So it will not be drawn above the x-axis. It will be drawn below the x-axis, right? Because here the electric field is positive, here that is negative, right? So graph goes negative like this, and when you go in this way, so towards the negative side, what is happening? The electric field is towards the positive side. It goes like this, right? So this is the basic variation of Ex curve for a positive charge as well as for the negative charge, towards right and towards left. This is how it will look, right? Now, if you have two positive charges and you want to show the Ex curve for that, so how will you show that? We have one positive charge, so it will have electric field like this. So where will it go? It is above or below the x-axis. We can say, since it is towards the negative side, it will go in this way, right? So in this region, you will have the electric field variation going on. How will it vary, right? We can say that in this region, the electric field vary like this, so it is like this, right? So this is how it will happen, right? So we can draw it better, right? So I believe the idea is very, very clear. In this side, we can have this way. For this way, when you are moving in this direction, so if we are moving towards positive side of the axis, electric field is also in this way. So it will be above the axis like this, right? It will move like that, right? So we have a positive charge and a positive charge, but we have a pair of like charges, and you know that when we have a pair of like charges, there has to be a place between them where the neutral point is achieved, right? Where the neutral point is achieved, imagine a positive charge, unit test charge. So this one is repelling it, this one will also repel it. Let's say that here you achieve the neutral point. So what will happen? It will become 0 till here, right? And for this one, what will happen? You are moving towards this way, electric field is towards this way. So this is how it will look, right? And when you're moving in the opposite way, what will happen? When you're moving in the opposite way, what will happen? Electric field is like this. So it will go below the axis, right? Below the axis, like this. So I believe the idea is very, very clear. This is how the graph will look like when we have a pair of like charges, right? This way. Similarly, for negative charges, it will look like this, right? You can draw it, right? And if you have a positive and a negative charge pair, again, with the same reasoning, you can draw the graph for a positive and negative pair as well, right? Clearly, you can see that there is no region here in between them where the electric field is 0, right? Okay. Now we have the electric field due to the continuous charge distribution. Now we have the electric field due to the continuous charge distribution. So let's have a look at that, right? Here we have continuous charge, right? Okay, continuous charge distribution over a plate, over a wire, over any body, right? And you want to know the net field over here at point P, right? And you want to know the net field at the point P. How can you do that, right? So in this situation, there is a certain pattern we follow, right? When we want to know the value of electric field due to the continuous charge distribution, there is a certain pattern we follow, right? And this pattern uses calculus, little bit of calculus, right? So even if you are not strong in calculus, you can understand that. Very simple method you have to follow, right? Acha. In the same chapter, when you will understand Gauss's law, I will teach you by the end of this class. I'll also explain Gauss's law. And we can also calculate the electric field by continuous bodies by applying that Gauss's law you are going to learn, right? And that is also very easy, right? So if you want to understand the calculus part, you can go with this way. And if you want to understand by using the Gauss's law, right, that also uses calculus, right? So you can go with that way as well, right? So this is it. So here, this is the step-by-step method. First of all, this is the charge distribution, right? A single charge would create an electric field at this point, right? So if I have a distributed charge like this, I will also be able to create the electric field at point P, okay? Now, to know the value of electric field due to this entirely distribution of charge, so first of all, I will take a small section over here, right? A small section over here. I will call that a small section has an area, let's call it dA. The whole thing has an area A, and this small section has an area dA. So this is small, the total thing has a charge Q, but this small section has a charge dQ, right? And with the help of this small section, I can get some value of electric field over here, that is dE, right? The whole thing might be creating the electric field E, but that little section is creating the electric field dE, right? So now, I will first of all calculate the value of electric field by that small section, and then I will integrate it over the entire surface, right? So first of all, you will find the dQ, right? Then you will find the electric field by that small section, and then you will substitute that dq into dE and then integrate it, right? Then integrate it. This is going to be our common method when we are going to calculate the value of electric field in upcoming scenarios, right? So here we have it. We have a straight wire, right? And the wire carries a charge on it. So the charges are not flowing. It carries some charge on itself. And the linear charge density on the wire is charge cube upon L, right? This is a linear charge density on the wire. And you want to know the value of, electric field created by the help of this particular wire, okay? So let's have a look at that, right? Electric field at the axial point. So this is the wire, and at the axis we have a point P. We want to know how much field is created at the point P, right? Okay, so you see that this is the axis of the wire, and you want to know how much field is created by this, all the charges available on the wire at the point P, right? So the initial end of the wire is at a distance r away from the wire, and the final end of it is at a distance L plus R away from the wire, right? Okay. Again, our approach will be same. First of all, if you want to know the electric field by the continuous distribution, imagine a small little section that has a charge dq, right? Get the value of dq and then get the value of electric field by that little element, right? Once you know the electric field by this element, integrate it for the entire length and get the value of net field, okay? This is going to be our approach. Let's have that. So this the entire wire is made by small sections. Each of them has a charge dq and each of them has a length dx, right? The charge of unit length of this wire is lambda, right? This length is dx. So how much charge will this particular portion have? So we can say lambda into dx. Unit length has a charge lambda. So dx will have lambda into dx, right? Okay. So we know that how much charge we are going to have in this small little section, right? Okay. Now let's calculate it, right? This section is at a distance x away from the place where we want to calculate the electric field, okay? Right. And you see that this x, the value of x can vary from the initial part of the rod here to the final part of the rod, which is here, right? Initial part of the rod is at a distance r, and the final part of the rod is at a distance L plus R, right? So you see that this x is varying from R to L plus R, right? So first of all, calculate the value of electric field by this small little charge dq, right? So you see that dq is this lambda into x, right? This is what we have calculated, right? So the value of dq is going to be, this is the linear charge density into length of this thing, lambda into x. What is lambda? The total charge available per unit length. This is the value of the charge available on this little segment of the wire, all right? So q upon L into dx, right? So how much field is created by this small segment? We can say that it is kq by r square. I can consider, because this segment is very small, I can consider that as a point charge. So it will be creating, the electric field is kq by r square, kq by x square, right? So now if I integrate it over the entire length, what will I get? The net field is going to be integration of this thing. So if I integrate it over the entire length, so you see that the value of x, the value of x varies from r to L plus R, right? So r to L plus R, as I have already told you. So once you integrate it, you can get the value of net field, which is this kq by L, 1 upon r minus 1 upon r plus L. So all these things will be available in your notes, and I believe the approach of this derivation is also very clear to you, that how are we deriving it, right? So let's move on and talk about the next idea. So this is the electric field at an axial point, kq by L. L is the length of the rod, 1 upon r minus 1 upon r plus L, right? Okay. Now if we are at a point that is not on axis, it is a non-axial point, and this is not equatorial plane as well. If I had a rod and I consider the middle point of the rod and then I move here, so that is the equatorial plane. I'm not here at the equatorial plane, I'm anywhere at a random place which is not on the axis, right? So here I am at a point P, which is at a distance r away, perpendicularly r distance away from the wire, and I want to know how much field will be created at the point P due to the charge available on the wire of length L, right? And this point P is of course not on the axis, right? So you see that here what I have done, I am joining this end and this end. This end, let's say, is subtending an angle alpha, and the other end is subtending an angle beta, right? And now let's calculate it, right? Now let's calculate it. Again, take a small element, calculate the electric field here due to that small element, then integrate it from this place to this place. Right now, you see that the angle over here is changing, right? So if you know the value of electric field due to this element, right, and you see that this limit will work well, right? So here alpha to beta, right? So these limits are going to work really well for us, right? So just do that. So you see that, you see electric field due to that small element is going to be kq by a square. Let's say that this small element is at a distance a away from the point P, so kq by a square. And to know the value of a, you can use this triangle, right? And you see you can get the value of a is r by cos theta, r by cos theta, r by cos theta, right? Okay, so just put the value of a and you know the value of a in this situation, right? Okay, so dE is figured out. Now the value of dE is in terms of theta, which is in our case, because theta is something that varies from alpha to beta, right? Okay, so just integrate it from alpha to minus beta. Alpha is in this way, beta is in the other way, that's why we are calling it minus beta. So just integrate it with the proper limits and we will get the answer, which is this, kq upon Lr cos beta minus cos alpha. This is the value of electric field which is parallel to the wire, right? You see that at this place electric field is also parallel and also perpendicular, right? So the parallel component of field is this, the perpendicular component of the field is, we have also calculated that part. The perpendicular component is dE cos theta, so the perpendicular component is also this, right? So we can summarize it. When we have a wire and we have a point P on that somewhere near the wire that is not lying on the axis of the wire, so the electric field at the point P, which is parallel to the wire, the component of electric field parallel to the wire is this, and component of electric field perpendicular to the wire is this, right? Okay, now we can have different cases out of it, right? We can move this point P exactly on the equatorial plane, so alpha and beta will come out to be the same. Put alpha and beta same, this will be subtracted and parallel component will vanish. So if it is on the equatorial plane exactly in the middle, we will not have a parallel field over here, we will only have perpendicular field. Just put the value of alpha and beta as theta and theta same, right? So just they will be added up, right? 2 times sine theta. So I believe the idea is very clear. If it is on the equatorial plane, this will happen, right? You see that this will cancel out, right? So electric field in the parallel component will become 0 and we will only have electric field like this, right? So net electric field is this. So I believe the idea is very clear. If the rod is infinite, if the rod was finite, my dear kids, and you are standing here, so this was making an angle alpha and this was making an angle beta, right? If the rod is increasing, what will happen? Alpha will increase further. If the rod further increases, alpha will increase further. And the rod goes to infinity, alpha will continue to increase and it will become 90, right? So similarly goes on for beta as well. If the rod continues to increase here as well, so beta will increase and become 90. So in the same formula that we have understood, right, just put alpha and beta as 90. So parallel component is 0 and perpendicular component is 2k lambda upon r, right? This is an interesting and useful formula, right? 2k lambda by r, we will take this particular case. So all the cases cannot be understood with the help of Gauss's law. Gauss's law has a limitation when you calculate the electric field. Unlike this one, this calculus method is applicable in all cases, right? So here we have it, 2k lambda upon r, right? So electric field due to the semi-infinite rod. So a semi-infinite rod, that means the upper end is making an angle 0, the lower end is making the angle 90 degree because it is finite in this way, right? And the above end, upper end is visible to us, so that is making an angle 0 degree, right? In the same formula, just put the values, alpha is 0, beta is 90, right? Same formula, put the values. You will have the parallel component and perpendicular component, perpendicular component written over here, right? Okay, so now let's talk about the electric field in the case of a uniform uniformly charged ring, right? So uniformly charged ring. So I have a uniformly charged ring like this, right? I have a uniformly charged ring like this. So what will happen? We want to know how much electric field will be there at the center of this ring. So think about it. If I assume a little section over here and I assume a little section of the same length over here, both of them will have the same charge because it is uniformly charged. Now it's a positively charged. Imagine a unit test charge over here. This section is going to produce the electric field in this way. Positive will repel it. And this section is also positive, will repel it in this way. Since they are in the opposite directions, they will cancel out each other, right? They are in the opposite direction, they will cancel out each other, right? And they will have no net field due to these two sections, right? Similarly, I have a section here and opposite to that, I have a section here, right? So this is creating electric field in this way, this is creating the electric field in this way, they will cancel out each other as well. Similarly, I can have a section over here, I can have a section over here, they will also cancel out each other's electric field. I will have a section over here, I will have a section over here, they will cancel out each other's electric field at the center. So you see that for every section, I have a section against it that will cancel out the net electric field at the center, and that's why we know that due to all these sections, the net electric field over here is going to be 0, right? Then due to all these sections, the net electric field over here is going to be 0. I believe the idea is very, very clear, right? Okay. Right, I believe the idea is very, very clear. Right, so now what we are doing to, at point C, the electric field turns out to be 0. So we are now moving on the axis of the circular ring. It is a charged circular ring. And now we are moving on the axis of that ring to calculate the value of electric field, right? So again, the approach is same. Take the small element, calculate the electric field over here due to that small element, and then integrate for the entire wire, entire loop, right? So for this element, I will have electric field, just join them. Electric field in this direction, I can take two components, right? And similarly, against that element, I have a mirror element over here. So it will create the electric field like this. So it will again have a vertical component and a horizontal component. So see that over here, the vertical components will be cancelled out, right? Vertical component even on the axis will get cancelled out, but the horizontal components keep adding up, right? Horizontal components where due to all the elements keep adding up. So the net field is only going to be along the axis because the vertical component, as I said, will be cancelled out by some other mirror element, right? So this is what is written over here. So dE is dq by x square. So x is this, right? And dE sine theta will get cancelled for each element due to the mirror element. So dE sine theta will cancel out by this element, by the mirror element, you can say, right? Okay. So you have Ex going on for you, right? So we have only the Ex going on for us. This is this E dE cos theta, right? So just integrate it, right? Just integrate it and you will get the value of dEx, the net value of electric field with the help of this circular charge ring on the axis, right? Which is this, right? Now, if I take the approximation, if I say that the value of R is very, very large as compared to capital R, or the opposite case, value of capital R is large as compared to small r, in both cases, one can be ignored. That is small, that can be ignored, right? So if a small r is much, much greater than any the distance that we are figuring out is much greater than the capital R, right? Then what will happen? The formula will come out to be this, kq by r square. And if a small r, the radius of the loop is much bigger, then it is kqr by r cube. So I believe the idea is very, very clear, right? Now, what is the maximum value of electric field closer to this ring? The maximum value of electric field, for that you have to apply the concept of maxima and minima. Just differentiate the value of this thing and get the value of R where it is going to be maximum, right? So the maximum value is achieved, dE by dr is 0, right? And the maximum value is achieved at this place. R is plus minus R by 2, right? So when the value of R is either plus R by root 2 or minus R by root 2 from the ring, we have the maximum electric field near a circular ring on the axis, right? Okay, all right. And what is that maximum value? In the same formula, put the value of small r equals to root r by 2 and you will get that, right? Okay. So this is the variation, right? You can understand that the value of small r where it gets the value of electric field gets maximum, right? So you see that This is how the graph will look like. So it at small r equals to r by root 2, that is electric field is maximum, and over here also it is maximum, right? And then it is simply dropping out in this way, right? I believe the idea is very, very clear, right? Again, we can apply the same concept, take the element and integrate. Take the element, get the value of electric field due to that element, and then integrate for the available wire, right? And that's how we calculate the electric field due to the entire geometry. So for semicircular wire, again we take the element, calculate the value of electric field due to the element, and then integrate for the entire wire and get the value of net electric field due to the entire wire, right? So here we are going to have the same thing. So this is it. This is the net field over here due to the semicircular ring, right? Similarly, we can have a 1/4 of the ring. Again, the approach is same. Take the small element and get the value of electric field due to the small element and integrate, get the value of electric field due to the entire thing. So this is the electric field due to the, this is integrated, right? And this is Ex and Ey. So this is the net field over here, root 2k lambda by r, right? Okay, so the same things are going on. Now, if we have to find a generalized case, right? So we have a sector of a ring. So if I have a sector of a ring, not quarter ring, not half of the ring, not 1/8 of the ring, just a random section of the ring, then in that case, what will happen, right? In that case, what will happen? It is going to subtend some angle. That angle is alpha. And in terms of alpha, we can figure out, right? In terms of alpha, we can figure out, again, the approach is same, right? The approach is same, Ex and Ey we have figured out. So the net field is this, 2k lambda by r sine alpha by 2, right? 2k lambda by r sine alpha by 2. So just put the value of alpha in different situations. When it is a half ring, so alpha is 180. When it is full ring, alpha is 360. Just put the values of alpha over here and you can get the value of electric field for all other cases of the circular ring. All right. So this is what we have figured out, right? Okay. Now here we have motion of charged particle, my dear kids, right? Motion of charged particles, my dear kids. So what is happening over here? I have this charged particle, right, inside the electric field, okay? So electric field will apply the force on the charged particle, and you know by Newton's law, if you apply the force on a charged particle, its state of motion will change, right? Okay. How will the state of motion get changed? You see that, let's say a positive charge is there. I have electric field from a higher potential to a lower potential, right? So in this way that we have the electric field like this. So you see that this is the positive charge. It will be attracted towards the negative end of it, right? So you see that the negative end is attracting it like this, right? So it is going to move in this way. Good. So you say here, from here we can calculate the value of force acting on the charged particle. So how much force will be applied by the electric field E? We can say that E is F upon Q. So F is E into Q. This is the force applied by the electric field on the charged particle, right? Okay. And once you have the value of force going on in this situation, my dear kids, you see that a charged particle which is simply launched in the electric field with the initial velocity V0, how will it move, right? How will you analyze the motion of such a charged particle that is moving in the electric field? Understand, my dear kids? Motion of charged particle we talk about in the magnetic field in a different chapter. But here we are talking about the motion of charged particle in the electric field. So we have a positive plate and a negative plate. Between them we will have an electric field like this. And a charged particle is launched perpendicularly to that, right? So what will happen? A charged particle is launched perpendicular to that. So what will happen? So right now you see, the force on the charged particle will be acting, it's a negative charge, so it will be experiencing a force towards the positive plate, right? So this is how much, this is in which direction for the force will be acting on the plate, right? And the plate is moving like this, okay? It is moving with the velocity V0, okay? All right. So see that, is there any force in that direction? We will say there is no force in the horizontal direction, no force in the horizontal direction, in the horizontal direction. Horizontal direction or x-axis, right? So if there is no force on the x-axis, what does the Newton law say? We say that, it says that if there is no force in a certain direction, there will be no change in the state of motion in that direction. So there will be no change in the state of motion of that direction, right? So practically we can continue to move ahead and talk about the next part. there is no force in the horizontal direction, my dear kids. So what will happen? The charge particle, there is no force in the horizontal direction. So what will happen? The velocity of the charge particle in the x direction, the velocity of the charged particle in the x direction will not change because there is no force in that. Got it? The velocity of the charged particle will not change because there is no force in that, right? And it will continue to move like that, right? Okay. So this is the analysis of the motion, right? So we can analyze the motion along the electric field and perpendicular to the electric field, right? So you see that along the electric field, we have a force, so there will be an acceleration. There is a constant force, so there will be a constant acceleration. Perpendicular to the motion, there is no force, so there is no acceleration, right? Okay. All right. So right now what is happening? Let's say that we are moving the charged particle in a gravity-free space, right? So the effect of weight is we are ignoring right now, right? In this direction, the effect of force will also be there, but right now we are moving the charged particle, let's say, in a gravity-free space. So effect of gravity can be ignored. Otherwise, if you are moving in a space where the effect of gravity cannot be ignored, right? Then in that case, you can consider that as well and talk about the net force every time, right? So here it is, right? Here it is. So we have the motion along x-axis. So we have the force along the x-axis is 0, perpendicular to the electric field, and there is no acceleration. And force along the y-axis is, force is how much? QE upon mass of the charged particle, right? Force is acceleration in the y direction, sorry, it is not the force, it is the acceleration in the y direction is QE upon m, right? Okay. So yeah, this is the acceleration in the y direction, right? And there is no acceleration in the x direction, so this is going to be the net acceleration as well, right? This is going to be the net acceleration as well. So you see that. So when you analyze the horizontal motion, it is started with a certain velocity, it will end at the same velocity as well, right? So if it is covering at the distance x in time t, so you will say that s is ut plus half at square, where acceleration is 0. So s is equals to u, initial velocity, let's say it's v naught. So it is going to be time is x upon v naught, right? So how much time the charged particle will take to move from initial point to the final point? It is x upon v naught. Okay, this is the time it will take to move from here and there. And in the entire time duration, it is experiencing a force due to the electric field like that, right? And that force is moving it. So it will shift the charged particle from the original path by a certain value y. So what will be the value of y? Vertical displacement. Vertical displacement will be, displacement in the y direction is ut plus half at square. Initial velocity in the y direction was 0. So this part will be 0, right? Half at square. Acceleration you have already calculated in the previous page. It is QE upon m, right? QE upon m, t square. Time you have calculated how much time it took to move from here to there, right? So for all that duration, it was pushed in this way. So time you have already calculated x upon v naught. So just put the value of time as x upon v naught, and you can calculate the vertical displacement of this thing, right? So I hope the idea is very, very clear, right? And similarly, you can also get the value of vertical velocity at the end of the journey by using the third equation of motion, or first one. V is equals to u plus at, simpler, right? You can do that. Okay. All right. And at the end of it, the charged particle is here. It has acquired a velocity in this direction as well as in this direction. So you can get the value of net velocity, tan of theta is Vy upon Vx as well, right? Okay. Now let's talk about the last concept of this particular part, which is the electric field lines, right? So what is electric field line? As I said, Michael Faraday used a set of lines to represent the presence of electric field around a charge distribution, right? That they called as electric field lines. So you see that for a positive charge, the field lines are always outwards, and you see that the length of field lines is reducing. What does that represent? It represents the intensity of field reduces as you away from it, away from the charged particle, right? Okay. So unlike the magnetic field line, they start from the north pole and they enter into the south pole, they continue to move inside the magnet and they form a closed loop. But the electric field lines don't do that, my dear kids. They start from positive, they terminate at negative, right? Okay. So if I have a dipole like this, so electric field lines will move in this particular fashion, right? Okay. They originate from positive, they terminate at negative, right? So now there are some properties attached to the electric field lines. First of all, the tangent property. So if at any place you draw a tangent to the electric field line like this, at any place you draw a tangent to the electric field line, what does that represent? It gives you the direction of electric field at that place. At that place, at point P, the electric field here is here. At point Q, the electric field is here, right? Like that. Electric field lines, another property of electric field line is they do not form a closed loop. Just follow this line. It is moving in this way and it doesn't come back, right? So electric field lines do not follow the closed loop. Okay. So for two charges, electric field lines are always symmetric about the line joining the two charges, right? They are symmetric always about the line joining the two charges. Okay. So this is the line joining the two charges. They are symmetric, means they are always forming the same angle. Not very useful. For an isolated charge, electric field lines terminate at infinity. So this is a negative charge isolated in the space. They are terminating at infinity, right? Electric lines of forces are always perpendicular to the surface of charged body. Yes, this is very, very important, right? You see that they are always perpendicular to the surface of charged body. They are always perpendicular to the surface of charged body. If I have a charged body like this and the electric field lines, let's say it's a positive charge, electric field lines are shown in this way, you can say that this is a wrong diagram because these angles are not perpendicularly outwards, right? The next one is saying that for an individual charge, number of electric field lines of electric lines of forces is independent choice. Okay, yeah. You can draw that, right? Magnitude of charge is directly proportional to the number of electric field lines originating or terminating at that charge. So if you have to show that there is a 10 Coulomb charge and there is a 2 Coulomb charge and they are just giving you a figure where they are drawing a lot of lines around a 10 this like that, right? And the other one is drawn like that, right? So you see that this one has lots of field lines. So clearly this one is a bigger charge, then this one is a smaller charge, right? Okay. Number of electric field lines is proportional to the magnitude of charge. So more field lines means bigger charge we have, right? Electric lines of forces do not cross each other. Why is so? Because if they cross each other at a point, then at a point of intersection, what will happen? You see that at a point of intersection, what will happen? If I follow the line number 1, the direction of force or the field will be like this. If I follow the line number 2, the direction of field will be like this. At one point, a charge, a single charge cannot create field in two different directions at one point, right? A single charge cannot create electric field in two different directions at one point, which is why this is not a possibility, right? Electric lines of forces for two positive charges. So we have two positive charges and field lines do not, try and touch each other. They just become parallel, right? Number of electric lines of force per unit area or your line density represent the magnitude of electric field. We know that, right? So here the field lines are much closer, right? So field intensity is higher over here and the field gets weaker as you move further away, right? Uniform and non-uniform field. Uniform field, here you see that in a given area, you always get the same number of field lines. So this is a uniform field. In the same area, you don't get the same number of field lines. This is a non-uniform field. In the case of uniform field, the separation between the field line is same. In the case of non-uniform field, the separation between the field line changes, right? Okay. So this is a uniform field, this is a non-uniform field, right? I believe the idea is very, very clear. All right. So this is pretty much everything about the concept of electric field, right? Now let us move on and talk about the next concept. Now, after looking at the first two parts, now let us move on and talk about the part number 3. And you will find that in this list, the key idea of this particular part is Gauss's law, right? We want to know about the Gauss's law, which is more important, you can say, right? But Gauss's law talks about the concept of electric flux. So to understand Gauss's law, we need to know about the electric flux, right? An electric flux depends on two things, electric field vector and area vector, right? Now it can confuse us that why area is a vector. We will talk about that in the first part itself. So we will understand area vector, that will help us understand the second part, electric flux. That will help us understand Gauss's law. And finally, after knowing the Gauss's law, we will look at the application of Gauss's law. So this is the part number 3. So without any further delay, let us start with the first thing in the part 3, which is what is area vector. So let's look at that. Now, so far my kids, you know that area, we have never treated area like a vector quantity. For example, if we had a rectangle, we said multiply the length and width and get the area. If we had a circle, you can say radius of the circle is, let's say, is r, then pi r square is the area of the circle. So far, we always took area as a scalar quantity. But right now, you will see that area, it has some direction, right? So how to know the direction of area vector? Let us have an understanding of that, right? My dear kids, while solving a particular numerical, you are entirely free to take the direction of area vector in any two of these two ways, right? For example, if you have a given area like this, right? Imagine that this shaded part is your area. Then where is the direction of area vector? So you see that a line, a vector perpendicular to this way, right? Perpendicular to the given surface. This represents the direction of area vector, right? So if the area vector is like this, if the given area is like this, right? So area vector will be like this. If the area is like this, the area vector will be perpendicular to that, right? So the direction of area vector is always taken as perpendicular to the given area, right? Now you are entirely free to take the direction of area vector either towards this way or towards the other way, right? So you are entirely free to do any of that, right? So let's try and understand what is the area vector. You can say that for any given area, it can have two things like any other vector, right? One thing is magnitude, the other thing is direction. So if I talk about the area vector, it can have two things, magnitude, and the second thing is going to be direction, my dear kids, right? So the magnitude of given area vector is simply the area of the given quantity, right? So if you have a rectangle, right, then the magnitude of area vector associated to that is the magnitude of the given area, right? Length into width, right? It looks like a square though. Now the second thing is direction. So what would be the direction? Always perpendicular to the given area. So right now you can either take perpendicularly outwards or perpendicularly inwards. Just keep in mind that for that particular numerical you are solving, if you have taken perpendicular outwards as a direction of this area vector initially, then for the entire numerical problem, you have to keep it that way, right? All right, so this is it. Right, so this area vector is simply has two things, a magnitude, which is the magnitude of the area, and the direction, which is always taken perpendicular to the given area. All right. So after knowing that, we can apply this concept and try to find the area vector in this case. So right now we have a little rectangle. This side is A, this side is B, and this is X, this is Y axis, and we have to know the area vector in this case. So how will you know that? So again, this area vector will have a magnitude. So what will be the magnitude of area vector? Let's call this area vector is this, A vector, right? So magnitude of area vector is going to be this side and this side, right? So right now they are using a small a as a side. So I'll use capital A for the area vector just to keep things easier to understand. Magnitude of area vector will be side A into B, right? This side into this side, right? And what will be the direction? Perpendicular to the area vector. So this is x-axis. Unit vector along this axis is I cap. Unit axis vector along this axis is j cap. So we have to take the perpendicular. So it will be along the k cap, along the z axis. So either you can take along this way, k cap, or you are free to take into other way, like minus k cap, right? So the direction of this area vector will be k minus k cap, or you can say k cap. You are free to take any of that. This is or not divided, right? So if you want to write down this entire vector, so how will you write? You know that if a vector has magnitude A vector and the unit vector in this direction is, let's say, a cap. So a vector into a cap, magnitude of a vector into a cap, this represents the entire vector itself. So if you multiply the magnitude of a vector with a unit vector in its direction, you represent the entire vector, right? So if you want to know the area vector in this situation, so area vector for this case is going to be a into b is the magnitude, and in this direction the unit vector is k cap, or you can also put minus k cap, right? So AB into k cap, this is going to be the area vector for this situation. Let's look at that. Here you have a circle. Let's say the radius of the circle is r, right? This is x-axis, this is y-axis, this is z-axis. So now the magnitude of the area of this area vector, magnitude of this area vector is going to be pi r square, where r is the radius of this thing, and direction of area vector. So direction of area vector is perpendicular to the given area. So it is in this direction. This is the direction of area vector, right? So direction of area vector is along the x-axis. So along the x-axis, the unit vector is I cap. So this axis can be represented. The direction would be represented. Direction would be represented by I cap, unit vector along x-axis. So right now, how will you represent the entire vector? So right now you will say the area vector would be magnitude of area vector into unit vector in this direction, which is I cap. So you have pi r square I cap. I believe the idea is very, very clear. Let's move on and talk about this part. Okay, what is electric flux right now, right? So electric flux tells you how much of the electric field is associated with the given area vector, right? For example, try and understand that. I can have imagine that this is the entire room, right? And this entire room is filled with electric field, right? So imagine the electric field lines are moving from this side and they are moving towards this side. So electric field lines are moving from this side to this side, just like that, right? And now a lot of these electric field lines, and in this electric field lines, I'm placing a given area. Let's say that I'm placing this area like this, right? So you see that some of the electric field lines will be associated with this field, with this particular surface, right? Right now you can say that a lot of electric field lines are going to cut through the surface, right? And if I make the surface, the shaded surface like this, you see that the electric field lines will become parallel to the surface, right? Now you see that for a given area, the amount of field that is going to be associated to this given area depends on how big this area is, how big the electric field is, and also the orientation of this thing, right? How is this surface oriented in this particular electric field? If the area is parallel to the electric field lines are going to move parallel to it, and if they are at an angle to it, they will make certainly a different situation. Now, imagine right now, you see that right now you can say that with the common sense, if the electric field lines are moving like this, maximum electric field lines are going to cut through this surface. So we will say that maximum electric field lines are associated for this orientation of the surface, right? No problem with that. And in this situation, some kids get confused, and if I ask them what is the angle, what should be the angle between electric field and area right now? So they say that electric field lines are moving this way and surface is this way, so they take the angle is 90. That would be wrong, right? Try and understand that while calculating electric flux, we do not consider the angle between electric field and the surface. Electric field is moving this way and surface is like this, so we don't consider the angle between them, which is 90 right now in the calculation of electric field. So which angle is taken? Angle theta is taken between the electric field and the area vector. So where is the area vector? This is the surface, this is the area vector, right? So right now, if this is the electric field line which is moving this way, right now you can imagine this is the electric field lines and this is the area vector. So they are parallel to each other. So for this orientation of the surface, the angle between them is 0. So theta is 0 right now. So when you are going to calculate the electric flux, you will be using the angle theta. Theta is between the electric field vector and area vector. Theta is the angle between electric field vector and area vector. Where is area vector? Perpendicular to the given area. It is not the angle between surface and the electric field. It is the angle between area vector and the electric field. Got it? So let's say the orientation is changed like this, right? And for this orientation, what will happen? We will say that for this orientation, imagine the electric field lines are still this way. So electric field lines are like this, and the field is like this, right? Area vector is like this. So right now the angle is 90. Angle between area vector and the electric field is 90. Theta is 90 right now. Got it? So this is how we take the angle while the calculation of electric flux, right? So let's look at that. How to electric flux is telling us how much of the available electric field is associated with the given area in its current orientation, right? So let's say that the given area is a vector. What is this? Area vector. And the electric field available in this place, let's say, is E vector. The intensity of electric field is E vector, right? So the electric flux in this situation is a scalar quantity that is represented by dot product of these two things, E dot A, right? Now, if you open this up, it will become magnitude of electric field and magnitude of area vector into cos of theta. Theta is the angle between these two vectors. That is, theta is the angle between electric field vector and area vector. So right now, this should be noted. And this is where many kids do the mistake. So we'll be solving some problems on that as well, right? So note is theta is the angle between electric field this vector and this vector, electric field vector and area vector. Got it? And you can also extend it. It is not the angle between electric field and the surface. I believe the idea is very, very clear. Let us look at some problems and try to see how to apply this understanding of the electric flux, right? So let's look at that. As I said, flux is E dot A, so it's a scalar quantity, right? The SI unit of flux is voltmeter or Newton meter square per Coulomb. So we'll be generally using voltmeter because it is easier to pronounce, right? And dimension is this. Now look at this one. Find the flux passing from an area if magnitude of electric field vector is 20, magnitude of area vector is 5, and the angle between them is 60 degree. So we have to find the flux passing from an area. So the flux is going to be simply magnitude of electric field, right? You can write down like this or only E, right? Magnitude of electric field vector and magnitude of area vector into cos of angle between electric field, angle between them. Angle between them means angle between electric field and area vector, right? So angle between them is, right now, this 60 degree is the angle between these two vectors, right? So just put the values 20, 5, and cos 60. Cos 60 is 1 upon 2, right? Cos 60 is going to be 1 upon 2. So you see that? Answer would be 50 voltmeter. Okay. Now let us move on and look at another variation of the same problem. So here we have the electric field 10, area vector magnitude is 10, right? No problem with that. And the angle between surface and electric field is 60. In the previous question, they were giving us angle between them means angle between electric field vector and area vector is 60. And right now they are giving the angle between surface and electric field, that is 60, right? Remember that if this is happening, right, let's say the situation is like this. This is the surface, right? This is the electric field. The angle between surface and electric field, they are giving you this angle. This angle is 60. We are not interested in this angle. We are interested in the angle which is perpendicular to the surface, which is this. This is the direction of area vector. This is the direction of area vector, and this angle is something we are interested in. So total angle, you know that area vector is perpendicular to the given surface. So this angle should be 90. This is 60. So the remaining angle will be 30, right? So right now the angle between area vector and the electric field is going to be 30 degree, right? So the flux is going to be EA cos theta. So right now value of magnitude of electric field is 10, area is 10, cos 30 will be used here. Because the angle between surface and electric field is given, we want to know the angle between electric field and area vector, not with the surface, right? So 10 into 10 is 100, cos 30 is root 3 by 2, So it is 50 root 3. That is your answer. Voltmeter, right? So that is your answer. I believe the idea is very, very clear. Now let us move on and talk about the next part, which is this. Electric field is given this much. Area vector is given this much. Find the value of flux. Simple, right? The value of flux is E dot A. So right now they are given in the vector format. So you just put them as it is and take the dot product. 2i plus 3j minus k dot product 2i plus 3j and no k, right? So just take I and I, so that is 4, right? I dot product of same unit vector is 1, 3 and 3, that is again 9, and 1 and 1, 1 and 0, so basically 9 and 4, 13. There is no k component over here, so 13 voltmeter will be the value of the electric flux over here. Right now look at that. Find the flux if electric field is this. So electric field is given, right, and area vector you have to find out by looking at this area. So this side is given 10, this side is given 10. Remember that if they are giving you the units in centimeter and centimeter, we are calculating in voltmeter. Flux is calculated in voltmeter, right? And if they're giving in centimeters, you just convert them into meters, right? By multiplying with 10 to the power minus 2, right? So for now, they are not giving us any units, so we will assume that all of this information in SI units. So electric field is 2i plus 3j minus k, and this is 10, this is 10, right? So area vector will be 10 into 10. This is the magnitude, and what is the direction? We can say direction would be perpendicular to the xy axis, so it is k cap. You can also take minus k cap, but for now I am assuming it is outwards, right? So electric field is this way. So electric field is 2i, 3j and minus k. You have to take the dot product of these two things, E dot A, right? So you see that there is only k component and there is no I and j component. So this will be 0 when you take the dot product, right? So you see that 2i plus 3j minus k, right? And dot product you have to take with 100 k cap. So you see that I cap, there 0 I cap, 0 j caps, these two products will become 0 and minus and 100. So it will become minus 100 voltmeter. So I believe the idea is very, very clear. Minus sign is simply denoting that the electric field component is opposite to the direction of area vector that we have chosen, right? So minus sign is simply denoting the direction of the direction that we have chosen for that we have assumed the direction of electric field is perpendicularly outwards. So that direction is opposite to the electric field in this situation, right? So I believe the idea is very, very clear. Look at this situation. Find the net flux passing from the cone in the given case. So right now look at that. It's a closed surface and it's a good question, right? It will help us in so many ways when you're going to talk about the Gauss's law, right? When we have a closed surface, and the electric field lines are coming through that way, we have to know about the flux. So what do you get from the flux? What is the meaning of flux? So my dear kids, flux tells us how much of the available electric field is linked with the given orientation of the surface, right? Imagine I have a closed surface. Let's say I have a closed box like this bottle, right? And this bottle is entirely seal packed, closed, right? Okay. Now imagine how much of the water is associated with this water bottle. We will say that, let's say half a liter of water is already available inside, okay? And let's say that I place this bottle in the flowing stream of waterfall, right? Imagine that the waterfall is falling this way and I place this bottle like this, right? So how much of the surrounding water is associated with the bottle, right? Let's say that hundreds of liters of water is falling on this side. So hundreds of liters will fall away from on the other side. None of the water which is falling will go inside the bottle because it is closed, right? Yes or no? So if I have a closed surface, then the available electric field will not get linked with it, right? This is what we are talking about. This is the electric field, the waterfall that you have, and this is the closed surface you have. Whatever electric field lines will come from this side, all the electric field lines will leave on the other side. So they will not add up to the available flux. Imagine that the water is available inside this bottle is the net flux associated with it. So right now you see that the external electric field will not get linked to it, right? All the electric field lines that are entering from this side, they will exit on the other side. So they will not add up any value to the available electric field with this bottle, right? They'll not associate with the closed surface. So I believe the idea is very, very clear. Whenever you place a closed surface in the external electric field, the net flux which gets associated with the closed surface is always zero, because whatever electric field enters on one side, it leaves on the other side. I believe the idea is very, very clear, right? So the net flux associated with a closed surface placed in a external field is zero. Why? Because whatever flux enters on one side, whatever, this is a note you can say, this is applicable in the forward going problems as well. So whatever field enters on one side has to leave as well on the other side. Okay, right? So it will not add up to the available electric field with this particular closed surface. So the net flux in this situation is zero, right? Net flux in this situation is zero, and the Gauss's law exactly talks about that. So we will talk more about that. I'll show you a demonstration as well when we are going to discuss the Gauss's law. But for now, I believe you have some kind of understanding about the electric flux and the closed surfaces. All right. So let's talk about this part. Find the flux passing from the given surface if electric field vector is 2x I cap. Right, 2x I cap. So right now, electric field vector is given 2x I cap, means it is towards the x-axis like this. What would be the area vector? It is 10 into 10, and let's say perpendicularly outward is the direction, so 10 into 10 into k cap, right? So the area vector is 10 into 10 is 100, k cap. Electric field is 2x I cap. When you're going to take the product of these two things, the flux will come out to be 0. So right now, the net flux associated with this surface is going to be 0, and it is obvious as well that the electric field lines are, is toward I cap, means towards x-axis, and you see that the surface is placed parallel to that in this situation, right? Electric field, the surface is placed, the area vector is oriented in such a way that theta comes out to be 90, and that's why the phi is 0 over here, right? So here is this way. Find the flux passing from the given surface if the electric field is 2z k cap, right? So now you know the value of electric field, which is 2z k cap. So right now, if you move around the surface, what is the direction of electric field? The direction of electric field is around the k cap, right? And you see that the value of electric field changes with this parameter. This is the magnitude and this is the direction, right? So for different values of z, right? So when you move on the surface and you change the value of z, let's say this is the surface, right? And it is placed like this, right? So as you move for different values of z, right? Imagine that this is the z axis, this is the x axis, and this is the y axis, right? So as you move on this way, the value of z will change, right? The value of z will change, and for different values of z, the electric field will have different magnitudes. So right now, for this value of z on the surface, it will have some magnitude. For here, it will have some other magnitude, like that, right? So just like that, we have this value, and the surface is oriented in this way along the xy axis, right? So it's a very funny scene. Right now, area vector is this. So what is area vector? It is 10 into 10 into, let's say, k cap, right? So it is 100 k cap. So it can give you an illusion that both of them are in the same direction. So the flux should be, let's say, it can give you an illusion that flux is, let's say, 200 Z, right? But that would be an illusion, as I said. Why so? Because if you look at the value of electric field, right, it depends on the value of Z, right? Value of Z on the plane. And you look at that, for this entire surface, the value of Z is 0 because it is in the xy plane, right? It is in the xy plane, z-axis is outwards, right? Anywhere you go on the surface, the z doesn't change, right? And if that doesn't change, the value of electric field on this surface remains 0, right? On this surface, the value of electric surface field remains 0, and if z everywhere remains 0, then the flux has to remain 0 as well, right? Which is why I said it seems like it's a bit funny that if the value of electric field was something else, let's say 2z k cap plus something I cap plus something j cap, like that, right? Then we may have come across with some positive value. But right now you see that the value of electric field in this orientation, everywhere you go, there is no electric field, right? And for the entire surface is not receiving any electric field. So flux is just how much of the electric field is associated with it. No electric field can be associated for this particular situation, right? So it's a good question, right? Let's move on and talk about this part. Next part. Electric field vector is ax square I cap. Find the flux through the given cube. So electric field is along the I cap, means along the x-axis, right? Electric field is along the x-axis like this, right? So you have to find the flux through the given cube. How will you know that, right? We will say that the flux right now, it's a closed surface. So whatever electric field enters on the one side, same electric field has to leave on the other side, right? So the net flux has to remain 0. Net flux has to remain what? 0. I believe the idea is very, very clear. Net flux has to remain what? 0. All right. Now let's move on and talk about the next idea. Question is, consider a uniform electric field 3 into 10 to the power 3 I cap. Okay. Uniform electric field is given 3 into 10 to the power 3 I cap, Newton per Coulomb. All right. Question is, what is the flux of this field through a square of 10 centimeter on a side? Now, hold on. They are saying 10 centimeter, right? And as I said, we are always calculate in the SI units. So the magnitude of area vector, we have a square, right? We have a square with a side 10 centimeter. So magnitude of this square will be 10 into 10. It is centimeter square. So multiply with 10 to the power negative 4. It is now meter square. So it is 10 to the power negative 2 meter square. This is the magnitude of area vector. This is where many kids do a little bit of calculation mistake, right? So we have to, and they are also telling us the plane of this square is parallel to the YZ plane. So if it is parallel to the YZ plane, think about it. This is X, this is Y, this is Z. If the plane is parallel to the YZ plane, so what will be the direction of area vector? So direction of area vector is along the x-axis, which is I cap. So direction of this thing is, direction of this area vector is, direction is I cap. So how will you write the area vector? Area vector will be the magnitude into the direction. So we will have 10 to the power minus 2 I cap. I believe that is very, very clear. So we have electric field vector and area vector. And now we need to know the flux. Just take the dot product of these two. We have I cap and I cap. It will become 1. So 3 into 10 to the power 3 into 10 to the power minus 2, right? So in the first case, this is the first part, A. So what will happen? The flux would be electric field vector and area vector, the dot product of these two things. Electric field vector is 3 into 10 to the power 3 I cap. Dot product we have taking with 10 to the power minus 2 I cap. All right. So just multiply them. We will have 3 into 10 to the power 1. I cap and I cap will already become 1. So that is 30 voltmeter. All right. So this is the first part. There is another part as well, part B to it. What is the flux through the same square? If the normal to this is normal to this plane makes an angle of 60 degree with the x-axis. Normal to this plane is making, right? It is not the angle between the plane at the electric field vector or plane of the anything else, right? It is the angle between normal to the plane, that is area vector and x-axis. It is the angle between normal to the plane, that is normal to the plane is area vector, normal to the plane and the x-axis. And you see that along the x-axis we have electric field, right? So indirectly they are telling us the angle between area vector and the electric field is 60 degree. right? Listen one more time. They are giving us the angle between normal to this plane and the electric field and the x-axis, right? Along the x-axis we have electric field. You see that this many I cap. So that is electric field is along x-axis, right? And normal to the plane, that is area vector. So they are giving us the angle between area vector and the electric field, which is 60 degree. So again, for the same formula, we have EA cos 60. All right. So magnitude of electric field and magnitude of area vector into cos 60. Just put the values, right? Magnitude of electric field is this, 3 into 10 to the power 3, right? Magnitude of area vector is this, 10 to the power minus 2, and cos 60 is half, right? So just multiply them. You have 30 by 2, which is 15. So I believe the idea is very, very clear. Now this concludes the idea of electric flux and area vector. Now we are capable enough to talk about the concept of Gauss's law. And for that, I have a demonstration ready for you. So we will talk about that as well. Now let us move on and talk about the Gauss's law. Now the next part is Gauss's law, and you'll find that Gauss's law is very, very interesting, right? I have so many interesting demonstrations to explain all the ideas that we're going to talk about the Gauss's law, right? So let's have a look at that. So first of all, you will see that this is an image, right? Is this a Gauss's law? Is this Gauss's law? Is this Gauss's law? You'll find that all these images will help us to understand Gauss's law at a much deeper and intuitive level. Why and how? Let's have a look at that. So you see that Gauss's law talks about a closed surface. But the question here is, why the hell we have to talk about the closed surface at the first place, right? So this is why we are going to talk about the initial these pages, right? So let's talk about that. Try and understand that here the flow is happening in one direction. The liquid is falling, liquid is falling like that. And if you want to capture all the water that is falling, how will you do that? We will say, I can use an open surface like this glass, and I can capture all of the fluid which is flowing this way, right? Similarly, if I have a multi-directional flow, I have created some holes in it and the liquid is coming out in all directions. So it is a multi-directional flow and I want to capture all of it, all of this flow. So how can I do that? By using a larger bucket like this, it is still an open surface. I can capture all the flow which is coming out of it, right? So multi-directional flow can also be captured with an open surface. But what about this bulb? Look at this bulb. Imagine the light rays that are coming out of a bulb are representing electric field lines that would be coming out of a charged particle. Just like electric field lines will be going in all directions, so it's an omnidirectional flow. Light rays are moving out in all directions from the bulb as well. And if you want to capture all the light rays, can we use an open surface like this jar? Think about it. Here I have a jar without a lid. Can I capture all the light rays with the help of this jar? You will say no, right? So what is the best surface in the case of omnidirectional flow? So my dear kids, the answer is very, very obvious that if I have an omnidirectional flow like this bulb is throwing out all the light rays in all the directions, and if I want to capture it, the best shape is like this, right? So right now you see that I have used this bag and I have captured all the field lines. Here the light rays are there, but imagine that we have a charged particle throwing out the electric field lines in all directions and I want to capture it. So the best shape is this particular shape, this closed surface, right? So this is why the Gauss's law talks about a closed surface, right? Because it deals with the charged particles around and the electric fields of the charged particles, right? So here it is. So you have this charged particle Q, and now you want to know how much flux is associated by a closed surface, right? How much electric flux is associated by a closed surface, right? By a closed surface that encloses this small charge Q. Think about it. How much flux is associated with the closed surface that contains the charge Q? So we will say that the flux associated with the surface, this closed surface, the flux associated with the closed surface, or we will say the net flux associated with the closed surface is charged and closed within it. So charged and closed within it, charged inside the surface upon epsilon naught. This is what Gauss's law says. The net flux through a closed surface, right? The net flux through a closed surface is 1 upon epsilon naught times the charge enclosed within it, right? Okay. So if the surface contains more charge, right? So more flux will be associated with it. Makes sense, right? Okay. Now imagine a situation where we have lots of charge. So let's say we have three charges over here, Q1, Q2 and Q3. And we want to know how much flux is associated with this closed surface. So let me try to highlight the surface itself. So imagine that this is a closed surface, right? And it only encloses the charge Q1 and Q2, and Q3 lies outside. So we want to know how much flux is associated with this closed surface. So with the help of Gauss's law we can understand, right? Because Gauss's law help us understand the value of flux, electric flux associated with the closed surface, right? So this is the closed surface and you want to know how much flux is associated with it. So let's have a look at that. Now, if I want to talk about the electric field, right? So if I consider any point over here on the Gaussian surface, at this point, the electric field or the net electric field is due to all three charged particles, right? Make no mistakes. At this point, the net electric field is due to all three charged particles. But what about electric flux, right? We are not talking about electric field here, my dear kids. We are talking about the net electric flux at this place associated with this closed surface. So what is that? So net electric flux is, the net electric flux is charged enclosed within it upon epsilon naught, right? So what is the charge enclosed within the surface? We will say only Q1 and Q2 are enclosed while Q3 is not. So the charge enclosed is only Q1 plus Q2, right, upon epsilon naught. So this is the net flux enclosed, you get net flux associated with this surface. So you'll say that, sir, if the charge Q3 is creating the electric field over here as well, so why this charge Q3 is not contributing to the net flux over here, right? So why we are not adding Q3 over here as well, right? You'll say because, sir, it is only the charge enclosed and we have learned it by heart that we only consider charge enclosed in the numerator. That's why we only add Q1, Q2 and leave Q3. But that's you have by hearted it, right? This is not intuitive. Why only Q1, Q2? Why not Q3? So let's have a look at that as well. Right, so with the help of a little demonstration, we can understand as well. So imagine that it's a closed surface. It is closed from all directions. So it will work as a legitimate Gaussian surface, right? Okay. And now understand, imagine we have a charged particle like this. So you see that this charged particle lies outside the closed surface, right? Think about it. If the light rays coming out of this bulb representing, let's say imagine, they are representing the electric field lines of coming out of this charged particle, right? Imagine there's a positive charge and the light rays are the electric field lines. So you see that whatever electric field lines are entering on one side, all of them are leaving on the other side as well, right? So you see that if you take a Gaussian surface outside the charge, whatever electric field lines enter on one side, all of them have to leave on the other side, right? So what is the net flux associated with it? We'll say the net flux is zero because whatever entered, the same left, right? So this is the idea behind it. So let's have a look at that, right? So this is the idea behind it. So the net flux due to the charge outside is zero. That is why it is not used in the numerator. Now, many times, my dear students, you will find that this particular part is used. What is that? And why are we using it? Let's have a look at that as well. So this is going to be very, very useful, this particular notation. So let's have a look at that as well, right? So my dear kids, you know that the flux is E dot A. So if you have area A, right, placed in the electric field of intensity E, right? So the flux associated with the area A is E dot A, right? You know that. And we have discussed area vector and all those things, right? But if I have a closed surface of a random shape, imagine it's a closed surface, it's a closed surface of a random shape like this bag, right? It's a closed surface, right, like this bag. So I cannot draw in 3 dimension, but imagine that it's a closed surface like this bag, right? So here what is happening, okay? Imagine there is a small area on this closed surface and we are calling that small area is dA, right? And this is the area vector. This is the direction of this thing, right? This is the direction of area vector, right? Okay. So now how much flux is associated with this small segment? If let's say the charge enclosed is Q and it is creating the electric field E, right? Like that, right? It is creating the electric field E. So what is happening? The flux associated with this small section, right, d phi, is going to be E, like area is A, but here the area is dA, so it is E dot dA, right? From this small section, the flux associated is E dot dA, right? And if you want to know what is the net flux associated with this entire thing, so what do? You integrate, right? So you integrate the whole thing. You integrate the whole thing, right? E dA, right? And from where to where you integrate, right? You know that whenever we use integration, we use limits of integration, right? We want to integrate from here to here. And here, we want to integrate this over the entire closed surface. And for that, we use this notation, integration over the entire surface. And when we integrate it over the entire surface, so EDA over the entire surface will tell us the total flux of this. So this is the net flux of this thing, right? This is how you write it, okay? So in the upcoming part, when we will talk about the application of Gaussian Gauss law, when we will talk about the application of Gauss law, we will use this notation multiple times, right? And it should not scare you at all, right? What are we doing basically in this notation? We are talking about the net flux, right? We have a small element. EDA is the flux through that small element, and we have integrated over the closed surface to find the total flux through the entire closed surface, right? This is what we have done, right? Okay, so yeah, so here in the previous page, we have 3 charges. All of them are creating the electric fields E1, E2, E3, let's say, right? So every charge creates electric field now. So they are creating electric field E1, E2, E3. So as I said, over here, the electric field will be due to all 3 of them, right? In the first part, I have told you that if there are multiple charge particles, so here if you have to find out the net electric field, imagine a unit positive charge. It's a positive charge, it's a negative charge, it's a positive charge. So this is repelling it, E1, this is E2, and this is going to attract it. So the combination of all 3 of them will create the net electric field, principle of superposition, right? So electric field anywhere is due to all 3 charges, but the flux, net flux, is only due to the enclosed charges, right? Okay. So yeah, this is what we are talking about, right? So integration of E electric field in place of electric field, we have electric field due to all 3 of them, E1, E2, E3, and dot dA, right? This is what we have done. This is what we have denoted, right? So just a small concept of understanding. So let's move on and talk about the next idea. Here, the same things I have written as well, right? So electric field anywhere is due to all the available charges. Electric field is due to all the available charges, but the net flux, this phi is net flux, is only due to the enclosed charges, okay? This is what we have to remember, right? Because we have understood this part as well. Why only the enclosed charges contribute to the flux? Because whatever charges are on outside, they are not contributing anything to the flux. Whatever field lines enter to the closed surface, they have to leave on the other side through that closed surface as well. That's why we don't count them, right? So yeah. So here you have it, right? Here we have a closed surface. So here we have a cylindrical surface. The upper half is slightly transparent, so it might not be visible. But yeah, it's a closed surface, right? It's a closed surface. And this is a cube, right? Okay, it's a cube. So here you see that all 3 of these closed surfaces, right? It's a complete cylinder, it's a complete sphere, it's a complete cube, right? They enclose a charge Q inside them. So they enclose a charge Q inside them. What is the net flux associated with them? So we say the net flux is charge enclosed upon epsilon naught. With this geometry as well, charge enclosed upon epsilon naught. With this geometry as well, it is charge enclosed upon epsilon naught. You see that the net flux is not depending upon the shape of the closed surface that is enclosing it. And it is such a relieving factor. This factor alone should take the tension off your mind, right? That whenever you want to talk about the net flux, you are free to take any Gaussian surface, any closed surface, right? So now, if you have the option to take any Gaussian surface of any random shape, what will you do? We will say that we will take the easiest one that serves our purpose, right? So when we are going to talk about the Gaussian surface, right? Let's say that whenever we are going to assume the Gaussian surface from our end, we have seen in the previous page that the shape of the Gaussian surface does not contribute to the value of flux associated with it, right? So we are free to take or consider the shape of the Gaussian surface. Yes? Okay. So while considering the shape of the Gaussian surface, if we have to choose, we will take whatever is best for us. So what is best for us? The shape that we know about, right? We know the area of those shapes, we know the volume of the shapes, right? So, which is why we consider the shapes of the Gaussian surface should be symmetric, right? Whenever we think about the Gaussian surface, we try our best to think about a symmetric shape, right? For example, if I have to think about, let's say, if I have to think about, this is, let's say, a charge wire, right? Okay. And I want to imagine a Gaussian surface around it. So I have assumed a Gaussian surface like this, a small cylinder, like that, right? I have assumed a Gaussian surface like this, a small cylinder. I could have taken any random shape like this bag, right? I could have taken this section of the wire inside this closed surface, right? But I don't know the area of the random bag, right? I don't know the volume of the random bag, right? And it might create a lot of problems, right? So we try to assume a Gaussian surface which is symmetric, and we also make sure that the electric field it receives is similar, right, everywhere. For example, if we assume this kind of Gaussian surface, we will see that this part and this part are at equal distances from the wire. So they will receive, everywhere they will receive same amount of electric field. So everywhere they will receive electric field, same electric field. Electric field should be same everywhere, right? Same everywhere. So when we consider these two things while assuming the Gaussian surface for our calculations, whatever calculations we need to do, if we consider these two things, our calculations become simpler, right? We have option because in the previous page we have seen we can take any shape of Gaussian surface, right? But out of all the available options you have, what shape you will choose if you have the option? We'll say I'll choose an option where the shape is symmetric. So I know the area of the Gaussian surface. I know the volume of the Gaussian surface whenever I need. And I also want to a Gaussian surface that receives the same electric field everywhere, right? That can make my calculation easier, right? Okay. And now you see here the flux is only about the enclosed charges, right? So this is a very interesting idea. Here I have removed half of the Gaussian surface, right? Here I have removed a part of the Gaussian surface. You see that? So right now, upper half of the charge is not enclosed. It is above the Gaussian surface like this, right? So only half of the charge is enclosed, right? Only this part of the charge is enclosed, right? So only this part is contributing to the net flux through that closed Gaussian surface, right? So right now, in this situation, the flux through that semi-cylinder is charged enclosed. How much charge is enclosed? Not the entire charge. It is only q by 2. Half of the charge is enclosed. So q by 2 upon epsilon naught or q by 2 epsilon naught, you can say, right? Charge enclosed upon epsilon naught. This is the net flux, which is q by 2 epsilon naught. I believe the idea is very, very clear, right? From this situation as well, only half of the charge is enclosed, right? This charge, which is q by 2. So only half of the charge is enclosed, which is why flux through the hemisphere is q by 2 upon epsilon naught or q by 2 epsilon naught. Here in the cube we have 6 surfaces, right? And here I have only one, right? So if I'll tell you that if I have a charge through all 6 surfaces, the charge and the flux associated through the entire cube means all 6 surfaces was q upon epsilon naught. And here I have only one surface and this charge is there. So compared to this, how much of the flux will be associated with only one side of the cube we will say only one face of the cube. We will say 1/6 of that. Total flux was this, right? Q upon epsilon naught. And right now I have only one of those 6 faces, right? So only we will say 1/6 of the total flux will be associated with this side, right? So it is Q by 6 epsilon naught, right? So I believe the idea is very, very clear, right? Okay, so let's talk about this part. Now this is very, very interesting, right? This entire list I have created. So you see that these are the various orientations, right? So imagine that this is a cube, right? And they ask in the NEET exam in various different ways. So I have created a list, and I have inculcated all those cases in this one single list. It's a very important thing, by the way, right? Very interesting thing you can keep in your mind, right? So right now what are we doing? We have a cube. So let's say that we have a cube. So this is a cube, and over here let's say over here, yeah. So let's try to make a cube over here. So this side, and this is another side, this is another side, and this is another side. So it's a beautiful cube now. So now what is happening? We are assuming, let's say, the charge is placed at different places. So if the charge is fully inside the cube, so for this position, if the charge is fully inside the cube, then what will happen? In this situation, when the charge is fully inside the cube, then what will happen? We will say the flux associated with the cube is the closed surface. Cube is a closed surface. The flux associated with the closed surface is charged and closed upon epsilon naught. And right now, charge is fully inside. That is why it will enclose all of the charge Q, right? So it is Q upon epsilon naught, right? Q upon epsilon naught is the net flux over here, which is associated with this closed surface, okay? Now, the charge is at the center, right? It is at the center of the cube, again Q upon epsilon naught, but it is on the face. Right now, it is on the face. It is not exactly on the, inside it. It is on any one of the face, right? Like this. Let's say it is placed over here. Like this, right? You see that? It is on the face. So what will happen? Since you have placed the charge on the face itself, so half of the charge will be throwing out the electric field lines within the cube, and half of the charge will throw out the electric field lines above, right? In the air, right? So we will say that only this half is associated with this cube right now. So how much charge is enclosed within the cube? We will say it is Q by 2. So charged and closed upon epsilon naught. This is the net flux that you have, that you can say is associated with the cube if the charge is available on the one face, any one face, right? If the charge is on the edge, right? So where is the edge? If the charge is on the edge, so charge is on the edge. This is an edge, right? This is an edge. If the charge is on the edge, then what will happen? We will say that, you see, imagine that it's a charge like this, right? So you see that between these two faces, if I consider this face and if I consider this face, right? You see that only this portion of the charge is, will remain inside. Okay, this portion of the charge will remain inside, and if it is on an edge, so how much of the charge is that? So we'll say over here, if I had a face like this, so it will slice the charge in 2 parts. But right now, with the help of these two faces, I'm slicing it in 4 equal parts. So I'm only enclosing this section, which is Q by 4, right? I'm only enclosing this section. So this is the portion of the charge which is enclosed, right? Rest of it is going to be outside if it is on the edge. If the charge is available on the edge, we will say that only 1/4 of the charge is enclosed. So it is charged and closed upon epsilon naught. So Q by 4 epsilon naught is the net flux associated with this cube if it is on the edge, right? If the charge is on the vertex, right? If the charge is on the vertex is this, right? So if the charge is on the vertex like this, how much of the flux is associated with the cube, right? So you see that if the charge is on the vertex, we will say 1/8 of the cube, 1/8 of the charge is enclosed within it. You may imagine in this way, right? We have 3 faces, 1, 2, and this face, right? These 3 faces are slicing in this particular thing. You can have a lemon and you can try to cut the lemon in this way. You will find that you have the eighth portion of the lemon, right? You'll see that this is the lemon. You cut it like this, right? So this is half, okay? All right. Then you will cut it from this side. So this particular face has cut it like this. Now this side is cutting it like this, okay? So it is 1/4. All right, like this. Okay. This is 1/4 like this, okay? And now you have this side as well, which is cutting it. So it will become 1/8 of the entire lemon, right? So if I had the lemon, I would have cut it and I had shown you. But right now, I believe you can understand as well. You have only this little portion available at your disposal, q/8, right? I believe the idea is very, very clear. So if it is on a vertex, so it is q/8 epsilon naught. And if the charge is entirely outside, then it is 0, of course, because if the charge is entirely outside, whatever field line enter, the same have to leave. So though no charge is effectively enclosed by the surface, and by the Gauss's law, the flux will be 0, right? So this is it. It's a very simple thing, and I believe the idea is very, very clear, right? Okay. So now let's talk about one more idea. So these are all the problems, the same problems that we have already discussed. If the charge is at the edge, so only 1/8 of the charge is enclosed within it. Rest of the charge is outside. So here we have q/8. So here it is on the edge, 1/4 is enclosed, so q/4 upon epsilon naught. Here it is on the face, so half of the charge is enclosed, q/2 upon epsilon naught. Here it is on one face center, so it is q upon epsilon naught, right? Here it is on the center, inside, completely inside, so q upon epsilon naught, right? So right now you see that the electric flux through the surface in this situation will be, so this is a random surface in every shape, right? So you have the charge enclosed q in all cases. So how much flux will be associated with it? So we can say the shape of the surface is immaterial when we talk about the electric flux. So it is always q upon epsilon naught in all 4 cases, right? So we have the same situation going on. It is going to be the same in all the given figures, right? Okay. So have a look into this situation. A charge q is enclosed by a Gaussian spherical surface of radius capital R. Okay, the charge q is enclosed by this thing. Okay, the charge q is enclosed by this thing. All right. If the radius is doubled, then outward electric flux will be. If the radius is doubled, if you are doubling the radius, is that changing the value of enclosed charge? We can say no. If you double the radius, the enclosed charge still remains the same, and the flux associated, they are talking about the electric flux. So the flux associated depends on the charged enclosed, nothing else, right? So the charge enclosed remains same, which is why the flux and that is associated will also remain same. Here we have a dipole which is placed inside a cube. Find the flux through the cube, right? A good question. So we have the dipole, means the same two charges and opposite by nature, right? So what is a dipole? We're going to talk about the dipole in the, after the application of Gauss's law, we will talk about the electric dipole. So here we have two equal charges placed at a certain distance. If it is plus q, the other has to be minus q. This arrangement is called an electric dipole. The distance between them is assumed to be, let's say, 2a, right? So this arrangement is called as dipole, and this dipole is inside the cube. So what will be the net flux associated with the cube? So we will say that the net flux depends on the net charged enclosed within the cube. If you have a dipole, that means we have q and minus q, the effective net charge is 0. Q and minus q, the net charge is 0. So we have the flux, which is q plus minus q upon epsilon naught. So this turns out to be 0 upon epsilon naught. So the answer would be 0. I believe the idea is very, very clear. And let's move on and talk about the next idea, right? Which is the application of Gauss's law, right? So here we have lots of applications of Gauss's law where we are going to talk about the flux, and more importantly, we will calculate the value of electric field, right? We have already seen the value of electric field of these geometries in the first segment, right? But with the help of Gauss's law as well, we can calculate the value of electric field in different cases, right? Now, to be able to understand and to be able to apply the Gauss's law in all these situations, there are certain things you need to know, right? Because Gauss's law deals with a Gaussian surface, a closed surface, right? Okay. And Gauss's law also talks about how much charge is enclosed within the closed surface, right? Yes or no? Gauss law talks about two things: a closed surface, right? And how much charge is enclosed within the closed surface. So charge enclosed, right? So when you are going to talk about the application of Gauss's law, you will assume the closed surface that will be called as a Gaussian surface, right? Okay, Gaussian surface, and you will talk about how much charge is enclosed within the Gaussian surface, right? So primarily, when we are going to understand the application of Gaussian law, Gauss law, these are the two things we'll be calculating, and mostly our hard work will go into the calculation of enclosed charge for a given Gaussian surface, how much charge is enclosed within it, right? So we will try to understand intuitively. First of all, we will try to see how to calculate the value of enclosed charge so that we can apply it, right? Application of Gauss's law we are going to understand, right? And Gauss's law talks about these two things. If you don't know how to calculate the value of enclosed charge, how can you apply it, right? So I'll give you different situations, right? And we'll try to calculate the value of enclosed charge so that we will apply it. So when we are going to apply it, you will understand, right? So let's have a look at that, right? So this is what we have written over here. We have to understand application of Gauss's law. So for that, we have to talk about the charges enclosed and how to calculate them, right? So yeah. So here we have a cube, right? And this is a cube, right? And right now it's a hollow cube, right? It's a hollow cube. So you have the surfaces like this. You can imagine like this. It's a hollow cube like this box, right? Like this box, it's a hollow cube. And what is happening? You have provided a charge q to this hollow cube. So what is happening? Charge q is distributed on the surface of the cube. Charge q is distributed on the surface of the cube like this. Charge q is distributed over the surface of the cube. Okay. All right. So this is the charge we have given. Right. And now this is the situation where we have a hollow cube that has a charge q distributed all over it. And now just for our understanding purposes, we have assumed a Gaussian surface, right? Gaussian surface has to be a closed surface of any shape, right? And for our simplicity, because it's a cubic structure, we have taken a cubic closed surface, right, inside this thing, right? So now tell me how much charge is enclosed with this Gaussian surface that is inside the bigger cube, right? Now you will say, how much charge is enclosed by this Gaussian surface? Think about it. You will say, sir, as you said, it's a hollow cube. All of the charge is on the outer surfaces, right? How much charge will be inside? This will contain no charge, right? This will contain no charge. So this particular Gaussian surface encloses zero charge, right? Because all of the charge is outside, right? Okay. If I assume a Gaussian surface which is bigger than this cube, and again I am free to take any shape of Gaussian surface, but for my simplicity, I need to know a Gaussian surface. I can assume a Gaussian surface which is symmetric and that also receives a similar electric field over everywhere else. So for my simplicity, in this specific situation, it makes me feel better if I assume a cubic Gaussian surface, just like that. So you see that this bigger cube, encloses the entire geometry. So how much charge is enclosed? We will say the entire charge q is enclosed by this bigger cube. All right. Okay. Okay. Now, in the other situation, if this cube was solid, then the situation would have been different, right? Okay. If the cube was solid, let's say that we have a solid structure, right? And over here, we have this larger cube, okay, right? And we are giving this charge, and this is not conducting by nature. Even if it is a solid cube, let's say, right? If it is a solid cube, right? But if it is conducting, then what will happen? This is very important. If it is a conducting solid cube, then what will happen? Or any other shape for that matter, right? Not just cube, if it is a sphere or a solid cylinder, but if it is conducting, then what will happen? My dear kids, you will say, because conducting bodies have a nature that they allow the transfer of charges. So what will happen? If it is conducting and you provide this body a charge q, right? So what will happen? It will, charge q will be provided through a lot of charge particles, right? Okay. So you see that, you'll see the charges will repel and they will continue to travel on this conducting body as long as they can move, right? So how far they can move? We will say that they will continue to move unless they reach on the surface, right? Okay. So the charge particles, whatever you are giving the charge q through lots of charge particles, right? You just throw those charge particles to this thing and the total charge that you gave was capital Q, right? So what will happen? It's a conducting body. So charges will repel, because let's say you are giving a positive charge, so bunch of, right? Let's say you are giving a negative charge, so you are giving a lot of electrons, right? So what will happen? Lot of electrons are there. All of them have negative charge, right? It's a conducting body, so they will repel. If they are repelling, because it's a conducting body, it will allow them to move. Conducting body allows the movement of charges, right? So charges will move. And when will they stop moving? When they cannot move any further, right? You see that. They will continue to move and they will deposit on the surface. They will continue to move and they will deposit on the surface, right? Got it? Okay. You see that whatever charge you have given now, it has it is given through so many charge particles, right? Charged, charging or discharging of the body. When I was explaining, I told you that charging, discharging both happens through electrons, right? So to make it positively charged, you have removed electron. To make it negatively charged, you have provided electron. That part is done. But for now, you see that it's a conducting body, right? And all the charges that are available to it, if you are giving them inside somehow, so they will travel through the surface and all the charges will be available on the surface only, right? So nothing is inside, right? So even in that situation, if it is a solid conductor, you take a Gaussian surface inside, right? It's a solid conductor and you have given a charge on it. And if you assume a small Gaussian surface anywhere inside this solid conductor, so how much charge will that Gaussian surface enclose in itself? Again, zero, right? Because all the charge has already traveled to the surface. So nothing is there inside, right? Now, the most interesting case is there when the body is solid, but it is not conducting. It is non-conducting. So, if it is non-conducting and you are giving it a charge q, wherever you give the charge, it will stay there, right? So, you can also distribute the charge non-uniformly. You can make a lot of charge over here and you can give a little charge over here, make a lot of charge over here, make a little charge over here. You can put the charge over here, it is not going to travel anywhere else, right? You can charge this corner and it will not travel to the other place, right? It's a non-conducting body because, right? Okay. Now, since we have an option, right, and we want to understand a simpler version of it, so we have a non-conducting body, but we are not being cruel to ourselves, right? We are charging this body uniformly. So the charge q is distributed uniformly everywhere, right? The charge q is distributed uniformly over everywhere, right? Okay. The charge q is distributed uniformly everywhere, outside and inside. Everywhere the charge q is distributed uniformly, right? Okay. Now, we don't know the value of total charge that we gave to this body, let's say, right? But we know the value of charge per unit volume that we gave, right? We gave the charge per unit volume is, let's say, rho, okay? All right, rho. What is rho? It is volumetric charge density, okay? This is very useful term. It is charge density per unit volume, basically. How per unit volume, how much charge you gave, that is rho, right? The charge given, total charge if you gave q and the total available volume was v. So charge per unit volume was charge density. Okay. So once you know the charge, volumetric charge density, how much charge is enclosed right now with this Gaussian surface that you have assumed inside? So my dear kids, you will say Right now, sir, since the volumetric charge density per charge per unit volume is rho, and this is small cube has a side, let's say A. We have assumed a Gaussian surface of side A, that is a cube of side A inside it. So what will be the volume of this thing? It is A cube, right? So how much charge is enclosed within it? Per unit volume is rho, and the volume we have is A cube. So it is going to be total charge enclosed within the Gaussian surface. The charge inside the Gaussian surface will be volume of this thing A cube into rho. Got it? So I believe the idea is very, very clear. Right, let's have a one more case over here. Right, so here we have a wire, and this wire has some positive charge given to it. We don't know the length of the wire. It could be infinite. We don't know where the upper end goes. It goes towards plus infinity, and the lower end goes toward minus infinity. We don't know where it goes, right? But one thing we know, that the charge available per unit length, right? If I cut a unit section per unit length, how much charge is available on it? So that is what we can meaningfully calculate. So let's say that is lambda. Lambda is linear charge density. How much charge is available per unit length, right? What are we understanding right now? How to calculate the enclosed charge with the help of Gaussian surfaces, right? So linear charge density, that is how much charge is available per unit length. Got it? Now, in this situation, if we assume a Gaussian surface and want to calculate how much charge is enclosed within it, so I have assumed a Gaussian surface of cylindrical shape, right? Such that the center of the cylinder is aligned with the wire itself, right? So why so? Because the Gaussian surface we have to choose in such a way that they are symmetric. So cylinder is a symmetric geometry, right? And we have to consider a Gaussian surface that receives same electric field everywhere. So look at this side and this side. Both of them are receiving the same electric field. Good, right? So how much charge is enclosed by this Gaussian surface? Let's say the length of this thing is L. So how much charge is enclosed inside? How much charge is enclosed by this Gaussian surface? We are only interested in that part. So charge enclosed by this is, it has a length L, right? Okay. So per unit length, the charge available is lambda, and the Gaussian surface has length L, right? So we have the enclosed charge for this length, right? Per unit length, the available charge is lambda, right? And the Gaussian surface has length L, so lambda into L, that will be the enclosed charge, right? In this with this Gaussian surface, right? Take one more example. How will you calculate the value of, this is the most important part in the application of Gaussian and Gauss's law, right? Think about it. If we have a sheet, right? If we have a sheet and we are giving it charge uniformly distributed, charge is uniformly distributed all over it, right? Uniformly charge is distributed all over it. So we don't know anything else, but we know the charge density, right? So what is the charge density right now? So charge per unit area. So this is called, we can say that this is sigma, we can say, right? What is that? It is areal charge density. Areal charge density. All right. So what is that? Charge per unit area. Okay. Now, we have assumed a Gaussian surface again, right? And for this purpose, let us say that we are talking about a Gaussian surface. Think about it. Electric field lines are moving from the positive charge like this. None of the electric field lines are moving anywhere else, right? All the electric field lines are moving like this, right? So we don't have to care about the electric field lines moving this way, because we will not have the electric field lines moving this way. Positive charges will emit the electric field lines like this. So we need a Gaussian surface that can capture these electric field lines, right? So think about it. If the field lines are moving this way, it makes no sense to have a, surface which is placed here, right? It will capture nothing. But if I have a surface like this, it will capture all the electric field lines like this. Got it? So just place it. So think about it. So for this specific case, I need to imagine a Gaussian surface first. So what could be the shape of the Gaussian surface? So for that, I have assumed a little cylinder, right? And you see that this cylinder has three surfaces. Let's call this section is A1. Let's call this section is A2, right? And let's call this outer surface. This outer surface is A3, right? Okay. And now think about it. How much charge is enclosed by this Gaussian surface, right? We will say that this part which is hanging outside the sheet has no value. It is not enclosing anything. This is where the charge is enclosed, right? It has a cross-sectional area. Let's say the area of cross-section is AC. Area of cross-section is AC. So be it A1 or A2, it is AC only. Okay. Right. So over here, how much charge is enclosed? So charged enclosed or charge inside is, we will say, the available area is AC. Okay. And the charge per unit area is sigma. So sigma into AC, right? That is the charge enclosed by this entire Gaussian surface. Got it? This is the charge enclosed by this Gaussian surface. I believe the idea is getting more and more clear, right? So once you know how to calculate the enclosed charge, application of Gauss's law, that is the key idea, becomes very easy, right? This is what we are going to talk about. Let's have a look at the application of Gauss's law, because now you are ready, right? Let's have a look at that without any further delay. So this is the application of Gauss's law. So now in the application of Gauss's law, the first application we have is electric field due to infinitely long uniformly charged wire. So as I said, with the help of Gauss's law, we can know the value of electric field through various geometries and various charge distributions. Here we have a wire that contains a charge Q. We have distributed the charge Q all over it. We don't know the length of the wire though, it's infinite. The upper end goes towards plus infinity and the lower end goes towards minus infinity. We have no idea about the length of the wire, and we don't know the total charge given to the wire. But one thing we know, how much charge is available per unit length. So that is charge per unit length is linear charge density, which is lambda, right? So this is what we know. Okay. We want to know, if you stand at a distance r away from it, a small r, if you stand at a distance r away from the wire, how much flux or how much electric field will be there, right? How much electric field will be there? Okay. And you want to know that by the application of Gauss's law, right? Now, to apply the Gauss's law, you will talk about charge enclosed upon epsilon naught. Charge enclosed by what? A closed surface, right? Gaussian surface. So to know the value of electric field over here with the help of Gauss's law, first of all, you need to know where is the closed surface, right? Because it is charge enclosed upon epsilon naught. Charge enclosed needs a closed surface, right? So where is that closed surface? So wherever you want to find out the value of electric field, first of all, you will imagine a Gaussian surface passing through that place, right? This is what we do. So when we try to understand the value of electric field with the help of Gauss's law at a certain place, first of all, we have to imagine a Gaussian surface passing through that place. And when we are considering the Gaussian surface, the shape of the Gaussian surface makes no sense, makes no difference whatsoever. So you are free to choose any shape, right? So how will you choose it? You will choose in such a manner that it is symmetric and it receives same electric field everywhere. So your calculations are easier. So life becomes easier. So we are taking a cylindrical shape Gaussian surface that passes through the point where we are interested to find the value of electric field at a distance r away from it, right? Okay. So now we need to know, we have to apply the Gauss's law. Gauss's law is charged enclosed upon epsilon naught. So this Gaussian surface encloses how much charge? So this is what we are interested in, right? You see that this closed surface is like this, right? It's like this, right? It has upper part, lower part, and this part, right? So upper part, you look at that, the electric field lines are like this from the wire, right? And this is the surface, above part, the part of the surface like this, right? So area vector of this section is like this, right? Electric fields are like this. So angle between area vector and electric field is 90 for this one. And for this surface as well, area vector is like this, electric field is like this. For that also the angle is 90 degree. So for these two surfaces, if the angle is 90 degree, right? So these two surfaces, basically no flux is associated with these two surfaces, right? So only one surface remains, the outside one, the one that wraps around it. right? So the net flux associated is E dA cos 0, because the area vector is of course in this way, and it is also, electric field is also in this way, so theta is 0, so cos 0. So it is E dA, right? Okay, all right. So the net flux is E dA, so right, so integrated. Electric field is same everywhere, so it can come out of the integration sign, so electric field is here. And integral of dA, the entire area dA3 is how much? So 2 pi RH. You know that if you have a cylinder like this, so the outside surface area is 2 pi RH. So we have assumed a cylinder of length L. So in place of height, we have length L, right? And we are calculating at a distance r away from it. So the radius of the cylinder becomes r. So it is, the outside area is 2 pi r L, okay? All right, so the area is 2 pi r L, okay? So just multiply it. This will give you the value of net flux associated with it, right? Net flux associated with it, it is E into 2 pi r L, no problem. So through this entire Gaussian surface that you have assumed, this is how much flux is associated. Good, okay. Till here, Gauss's law helped you, right? Okay. Now you know that. Now you know that this is the value of flux associated with this Gaussian surface. Okay. Now, with you know that the Gauss law says, that tells you that the flux associated is charge inside the Gaussian surface upon epsilon naught, right? And the flux associated you have calculated is this much, E into 2 pi r L, right? So just put it, okay, and just put the value of charge inside. So how much charge is enclosed? So as I said, the linear charge density is lambda, right? And the length of this thing is L. So lambda into L is the charge enclosed, right? So charge inside is lambda L, right? Okay, so just put the value. Lambda L upon epsilon naught is this, that is equals to phi, which is this, E into 2 pi r L, right? Lambda charge enclosed upon epsilon naught, charge enclosed is lambda into L. Lambda into L upon epsilon naught is this, E into 2 pi r L, right? So by simplifying it, you can get the value of E. But rest of the part will go in the denominator, and you can get the value of E. It is this, right? Okay, so I believe the idea is very, very clear, right? 1 upon 2 pi epsilon naught, what is that, right? You know that 1 upon 4 pi epsilon naught, we call that as K, right? We in the electrostatics, we often call it K, right? So it is 1 upon 2 pi epsilon naught, it is twice of that, so it's a twice of K, right? So it is 1 upon 4 pi epsilon naught. So this is again, I have written 1 upon 2 pi epsilon naught, just like that. So it is twice of K, 1 upon 2 pi epsilon naught. You see that 2 and 4 will cancel out, it will become 1 upon 2 pi epsilon naught. So this is going to become K, so it is 2K upon R, okay. Now this tells us an idea that the value of electric field near a straight current carrying wire depends on the value of R, right? Depends on the value of R. You see that you see that K is constant, right? Lambda again is a constant linear charge density. So the value of electric field depends on the value of R. And how is that? Electric field is varying inversely with R, right? So if you have a straight charged conductor, right? If you not a current carrying wire, if you have a straight charged conductor, then what will happen? How will the electric field vary around it? If you have a straight charged conductor, right, the value of electric field will vary with this relation. E is inversely proportional to R. And for that, the graph looks like this, right? So if you move further away, so the ER graphs looks like this. I believe the idea is very, very clear, right? Now let's move on and talk about the next idea. Apply it over here as well. This is another application, right? You have a charge distribution over the sheet, and the charge is uniformly distributed over the sheet, where with the areal charge density is given as sigma, right? So sigma is areal charge density, the charge available per unit area, okay, Coulomb per meter square, okay. And you want to know at a distance x how much electric field will be there. So the first thing, you want to know that by the use of Gauss's law, right? So Gauss's law is charge enclosed by the closed surface upon epsilon naught. So first thing is assume the closed surface, and while assuming the closed surface, you are free to take any shape again. So what kind of shape you should take? So I have taken a cylindrical shape. Why? Because the electric field lines are parallel, right? So any obstruction placed like this makes no sense, right? So this side again becomes immaterial, right? Okay, and because the electric field lines become parallel to this, so this side captures nothing, okay, and only this surface and this surface capture the electric field line, okay, right. So now we want to know that how to calculate the value of electric field at a distance x away from the sheet with the help of Gauss's law. So first thing we have done, assume the Gaussian surface. Now the second thing we need to know about how much charge is enclosed within the Gaussian surface. So the charge is placed on the sheet over here. Charge is placed on the sheet over here. Per unit area, charge is sigma, and the area over here is area of cross section AC. So charge enclosed is AC into sigma. Got it? This is the charge enclosed. Got it? All right. So now all you have to do is calculate the net flux, right? And it is charge enclosed upon epsilon naught. You know the value of charge enclosed, equate them, and you'll get the answer, right? Value of electric field. So here you have it. You have three sides of this Gaussian surface. One is this side, one is this side, and the other is this side. You see that? The area vector is in this way, electric field in this way. So this particular side, which is wrapping in this way, right, has an angle 90 degrees. So this particular, for this entire surface, the flux associated is EDA. Let's say the area of this surface is dA3, right? The element on that is dA3. So we see that cos 90 is there. So the entire this side, this particular side has no flux associated with it, right? For this side, you know, the area vector is like this, right? So area vector and electric field vector is also outwards because it's a positively charged sheet. So electric field lines are like that. So electric field lines are parallel to the area vector. They are parallel. So theta is 0. Theta is 0. So phi is integral EDA cos 0, right? Okay. So same goes on for the other side as well, EDA cos 0. Got it? So just add them up. The net flux is going to be flux associated with this side, and the other side. Okay? So just add it. And the net flux to the cylinder is going to be E, because we have chosen the Gaussian surface in such a way that it is symmetric. It is also x distance away. So both of them are receiving the same electric field, right? Electric field is same everywhere, and this particular side has no flux. So that part is 0. Phi 3 is of course 0 because theta is 90, right? So just add them up. dA1 net area of this side, dA2 net area of this side, it is area of cross section, which is AC, right? So just multiply that and you put the value phi net flux to the cylinder will be 2E into AC. 2E into AC. I believe the idea is very, very clear. E integral of dA is AC, integral of dA2 is also AC, area of cross section, right? So you see that EAC and EAC, 2 of EAC, twice of EAC, right? This is the net flux associated with this thing, right? Okay. Now you see that with the help of Gauss's law, we know that flux associated is charge inside upon epsilon naught, and you have calculated the flux is 2EA, right? Charge inside is sigma into AC, right? Sigma into AC, right? Just put the value. Charge inside is sigma AC upon epsilon naught. That is equals to the phi, which is 2AC, right? I believe the idea is very, very clear. And now you can get the value of electric field from here. The value of electric field is sigma upon 2 epsilon naught, right? Sigma upon 2 epsilon naught is not depending on the value of x, right? So why so? You see that it is also very, very clear that all the electric field lines are parallel. So you see that if they are, and you know the properties of electric field lines, right? The place where the electric field lines are cramped up, it represents that the intensity of field is higher at that place, right? So you see that the electric field lines are parallel everywhere. That means the intensity of field remains same everywhere, right? And that's why that's what is reflecting over here as well. Electric field is not depending on the value of x, right? So I believe the idea is very, very clear, right? Okay, so let's move ahead and talk about this problem. What is the net electric field at points A, B, and C? If two infinitely opposite charged plane sheets having same charge density sigma are placed parallel to each other. So this is the question. I'll give you a hint and you can try by yourself as well, but I'll explain it as well. So you know that electric field, calculation of electric field requires you to assume a unit positive test charge. So when you are calculating the electric field at A, think about it, how will you do? Imagine a unit positive test charge over here. This positive sheet will repel it. This negative sheet will attract the unit positive test charge, right? And the net electric field will be superposition of these two things, right? So they are opposing each other. So you see that this particular sheet is producing the electric field sigma upon 2 epsilon naught, right? electric field due to a sheet of charges sigma upon 2 epsilon naught, and both of them have sigma charge density, and the other one is also sigma upon 2 epsilon naught. It really doesn't matter, it is closer to this one and further away from this one. Why so? Because both of them are going to create a uniform electric field. A sheet of charge creates a uniform electric field. So you see that both of them are opposite, so they will cancel out. So over here the net electric field will be 0. Similarly, over here as well, imagine a unit positive discharge. This will attract it, this will repel it, positive and positive. So net field will be cancelled out, right? Sigma upon 2 epsilon naught, sigma upon 2 epsilon naught. Over here, if you calculate at point B, so imagine a unit positive discharge, the positive will repel it and negative will attract it. So sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught. So it is 2 times sigma upon 2 epsilon naught over here, right? So due to this one, sigma upon 2 epsilon naught, due to this one, sigma upon 2 epsilon naught, and they are attracted, right? They are added up. So it is sigma upon epsilon naught at point B. Got it? So over here is 0, over here is 0, and at the center it is sigma upon epsilon naught. I believe the idea is very, very clear. Now let's talk about the next application, right? And with the help of this flow chart, it should be very clear that electric field due to the infinitely long uniformly charged cylinder, right? Uniformly charged cylinder. Now, cylinder can have so many different possibilities to itself, right? Cylinder and sphere both, these are the two applications you have to talk about in different scenarios, right? They will be charged and you have to calculate the electric field in them, right? So how will you do that? So you see that it's a cylinder. The first set of possibility is it's a solid cylinder but conducting. If it is a solid conducting cylinder, imagine it's a solid conducting cylinder, so the charges can move through it. All the charges given through this solid conducting cylinder will travel until they cannot travel anymore. So they will deposit on the surface. So they will travel and deposit on the surface. All the charges travel, deposit on the surface, right? So if you have a solid conducting cylinder, all the charges will deposit, come over the surface, right? So solid conducting this cylinder has the charges over the surface. Hollow conducting cylinder, it's a hollow cylinder but conducting. That is why it is going to be uniformly distributed. Charge will be uniformly distributed and it will be available over the surface, right? Again, over the surface. Hollow non-conducting cylinder, it's a non-conducting cylinder, but if wherever you give the charge, it will stay there only, right? So charges are available only on the outer surface. Clear? So you see that in all three cases, if it is a solid conducting cylinder, if it is a hollow conducting cylinder, or if it is a hollow non-conducting cylinder, right? In all three cases, the charges always reside only on the outer surface, right? Now, you will also calculate the electric field in the case of solid cylinder, right? But it is non-conducting. If it is a solid cylinder and it is non-conducting, that means wherever the charges are given, the charges stay at that place. So even if they are inside, they will remain inside, okay? So this is the difference, right? So they don't travel to the surface, they stay wherever they are, right? Okay, so these are the cases that we have to talk about. The first thing is we have hollow cylinder, or hollow conducting, hollow non-conducting, or you can say a solid but conducting cylinder. So the charges are only available on the surface, right? In short, the charges are only available at the surface. For all the geometries, if they are uniformly distributed, this is the case, right? Chalo, let's talk about the next part, right? Let's say that since charges are only available on the surface, we are dealing with surface charge density or area charge density, sigma, right? Surface charge density or area charge density, sigma, right? Okay. Now, we want to know in different places, what will be the value of electric field, right? So, imagine we have this geometry. It could be a solid conducting, hollow non-conducting, right? So, hollow conducting or non-conducting, but it is uniformly charged. So, all the charges are available on the surface. Charges are available on the surface. Charges are available on the surface. Got it? Now, you can calculate the electric field in different situations, right? You can calculate the electric field inside it and outside it and on the surface itself as well, right? So wherever you want to calculate the electric field, with the help of Gauss's law, right? Gauss's law is charge enclosed by the closed surface, Gaussian surface upon epsilon naught. So the first thing is you need again a closed surface. The second thing is you want to know how much charge is enclosed by it, right? That's what the meaning of applying Gauss's law is. So you want to know the value of electric field over here. Case number one, imagine a Gaussian surface that passes from here. Case number 2, you want to know the electric field over here outside. So assume a Gaussian surface that passes from here, right? So this is in your hands, right? So this is the thing that you have. The length of this cylinder is immaterial, right? So the outer cylinder, the body that is available to us, that is a charged body, the length of this body is immaterial to us. So the upper end can go towards the plus infinity and the lower end can go towards the negative infinity, because we are dealing with the charge density, not the total charge. So charge density on the cylinder is, surface charge density is Q upon epsilon, Q upon area, right? Charge per unit area. Okay. Now, to know the value of electric field inside the cylinder, that is the distance from the center is small r, and you see that small r is clearly lesser than the radius capital R of the available cylinder, right? Okay. So for this situation, the first thing we have done, we have assumed a Gaussian surface. So this thing is a Gaussian surface, right? Right, passing through that point of interest. Okay. Now you look at that, the surface, or this part of the surface and this part of the surface, the area vector is perpendicular to the electric field lines, so they don't matter right now. You see that for these two cases, there is no flux associated with it, but right now we can directly look into it, right, without any discussion, a long discussion, we can say. So you see that all the charges on the surface, right, we have assumed a Gaussian surface which is inside. So all the charges are outside. Gaussian surface is there. So how much charge is enclosed by this Gaussian surface? Nothing, because all the charges are outside, right? So this Gaussian surface encloses nothing. So charge enclosed by the Gaussian surface is 0. And if the charge enclosed by the Gaussian surface is 0, so the flux associated with it is also 0. So the flux associated with this Gaussian surface is also 0, right? Okay, right. So the flux associated is this EDA. It is the flux associated, charge inside upon epsilon naught. Charge inside the Gaussian surface here is 0. So the electric field inside will also be 0. Got it? So if all the charges are outside the surface, there is no electric field inside. So that's a common sense. So with the help of Gauss law as well, we can say, right? So anywhere, if we are not able to capture the charged particles, right? So we will say that in this place, we will not have any electric field. Okay. So inside this thing, we have no electric field. But now if we want to talk about what is the electric field outside. So this is the hollow shell that we have, cylindrical, hollow cylinder we have, and we are interested in a place that is at a distance r away from the center. Okay. And we want to know the value of electric field at that place. So we have assumed a Gaussian surface. First of all, this is the shape of it. Okay. So first of all, we have assumed a Gaussian surface that passes through the point of interest, and again we have taken a random cylindrical closed surface, right, of length L, right? Okay. Now, first of all, we want to know the value of enclosed charge by this Gaussian surface. So you see that how much of the charge is enclosed by this Gaussian surface. So we say the charge is available on this side, right? Okay. Per unit area, the charge is sigma. Okay. So what is the area of this enclosed portion? We will say that it is 2 pi r L, right? 2 pi r L, 2 pi r L, right? 2 pi capital R into L. This is the area of the enclosed section, right? 2 pi r L, right? And per unit area of this section has a charge sigma. So the total charge which is enclosed by the assumed Gaussian surface is this. Total charge, this is the total charge enclosed, right? Okay. Okay, right. So now you apply it. Okay. Now you apply the Gauss's law. Right. So the total charge is this. So charge is this. Okay. So you have this part, right? You have this part. So total charge is this. It is 2 pi r sigma into 2 pi r L, right? Sigma into 2 pi r L. This is what we have seen over here. Sigma into 2 pi r L. This is the charge enclosed within the Gaussian surface, right? So Gauss's law, according to the Gauss's law, the flux associated over here is charge enclosed sigma into 2 pi r L upon epsilon naught, right? So now we have done the right part. Now what is the net flux? Think about that part as well. So net flux is integral of EDA. So integral of EDA means the flux associated with this part, flux associated with this part, and flux associated with this side of the Gaussian surface. This is the net flux associated. Put the value on the left side as well. So you see that this side has no flux association because the area vector is perpendicular to the electric field vector. Same goes for this side as well. So these two sides have no flux association. So all the flux associated is with this one as only, right? So how much is that? So we'll say the flux association is integral of EdA. And what is the angle right now? You see that the area vector and electric field vector are parallel. So angle will be 0 and cos 0 is 1. So E integral of dA. So what is integral of dA? So this is the closed surface integral. The Gaussian surface, this area of the Gaussian surface, the outside, this area of the Gaussian surface we are talking about. So it is having a length L and the radius at a distance R, we are calculating the things. So 2 pi R into L, right? So this is what we are talking about. Sigma into 2 pi capital R L upon epsilon naught, and integral of dA is let's use another page, right? Integral of dA is the whole thing, right? 2 pi R L. So small r is the radius of this Gaussian surface. Sigma into 2 pi R L. Sigma into 2 pi R capital L upon epsilon naught. So just try ahead, move ahead and solve it. So we have this cancels out. So electric field is going to be sigma into R upon epsilon naught, and this R will be over here. You see that? The value of sigma is the surface charge density on this available sheet, right? On the available cylinder, right? The value of epsilon naught is constant. The value of radius is constant, right? So see that the value of electric field is changing with R in this fashion, right? So as long as you are outside the cylinder, right, the value of electric field is inversely related with the distance from the center, right? Distance from this center, right? So if you are inside the cylinder, the electric field was 0, right? If you are inside the cylinder, electric field was 0. So in this region, electric field was 0. And as you step outside, electric field varies with inverse relation with the distance. Got it? So this is what we have, right? This is what we have. As you step outside, the value of electric field changes. So you see that the graph goes like this. Electric field is 0 in this region, and from this place, it moves like this. Electric field is inversely related to the R, right? So I believe E versus R curve is also very, very clear for the hollow cylinder or the solid conducting cylinder, right? And here you see that we have a solid non-conducting cylinder. So that means wherever you give the charge, it stays right there, right? It doesn't move anywhere else because it is non-conducting, and we are charging it uniformly, right? So let's say that in this situation, the volume charge density is given, and the volume charge density that is given is rho. So that tells us how much charge is available per unit volume, right? And again, you want to know the value of electric field inside and outside. So wherever you want to know the value of electric field with the help of Gauss's law, you need to know two things. First of all, the value there has to be a Gaussian surface passing from the point of interest. Let's say that we are interested in knowing the value of electric field at a distance r away from the center, such that R is inside. The point where we want to know the value of electric field lies inside the solid non-conducting cylinder. So the first thing you need to do is imagine a Gaussian surface that passes from the point of interest. So that is what we have, right? So again, you need to know two things: how much and charge is enclosed within it. So we have volume of the cylinder into the charge density, that is the charge enclosed by the cylinder, and now we need to know the value of flux associated with it. Now you just equate them and you'll get the value of electric field. So let's see how we are doing that, right? So we have taken we want to know the value of electric field at a distance r away from the center, right? And for that we are doing all the calculations. So we have charge enclosed upon epsilon naught. How much charge is enclosed? It is charge density upon into the volume of this particular thing. How much volume is there? It is pi r square into L. It has a distance r, length is L. So pi r square L is the volume. So this is the charge enclosed within it, right? Okay. So charge inside upon epsilon naught. So right side is figured out. Left side is how much flux is associated with the cylinder. So flux associated with this thing is in three parts. Flux can be associated with this one, or the other side, the outer side, right? So you see that these two sides have area vectors perpendicular to the electric field. So these two sides are not associated with the flux. Only this side is associated with the flux. So how much is that? Integral of EDA, right? Integral of EDA, you see that for this side it is 0. For this side again it is 0, right? Cos 90 is 0, right? And for this one it is integral of EDA cos theta. What is the value of integral of dA? Right, integral of dA is 2 pi r L, 2 pi r L, all right? So that's what we have, right? Just add them. The net cylinder is integral of EDA, which is E into 2 pi r L. This is the value of flux through that particular part, right? So this is it, right? So just add the values over here, right? E into 2 pi r L, this is the net flux, right? And charge inside upon epsilon naught is there. So charge inside is this, just put the value, rho pi r square L upon epsilon naught, which is this, into E into 2 pi r L. Just equate the phi and q upon epsilon naught and get the value of E from there. It is rho r upon 2 epsilon naught. You see the value of electric field is changing proportionally with the r. Volumetric charge, volume charge density, rho is constant, epsilon is constant, so E is proportional to r. So it is increasing linearly as you move away from the center. The value of electric field in this case of solid non-conducting cylinder increases linearly with the distance from the center, right? And similarly, if you want to measure the value of electric field outside, so again, take the electric field over here at a distance r away from the center, assume a Gaussian surface that passes through the point of interest, right? And the best shape of the Gaussian surface over here is another cylinder, right? And with the help of that, apply the value, how much flux is enclosed. Again, the flux enclosed is only due to this part, right? We will say that pi r square into L, L is this, and R is this R, pi capital R square into L. That is the volume enclosed by this thing into V, into rho, right? This is the volumetric charge density. That will give you the total charge enclosed, right? So this is it, right? Similarly, you can calculate phi 1, phi 2 and phi 3. Phi 1 is for this one, phi 2 is for this one, phi 3 is for this side, right? So thus add the value of these three things and you'll get the value of net flux. And once you know the value of net flux, you can get the value of charge inside upon epsilon naught, equate it, again you will get the value, and say the electric field changes, in an inverse proportionality with the distance small r. The distance from the center is small r. Capital R is the radius of that particular solid cylinder, solid non-conducting cylinder, which is the constant. So see that electric field changes inversely with the R in this situation, right? So see that for a solid cylinder, a solid non-conducting cylinder, the electric field increases proportionally or linearly from center to the surface, and then it drops in this fashion as you move outside, right? Okay. Now you have this particular situation where we have another sphere. And again, just like we have the cylinder, right, when it was conducting, right, but solid, if it is solid or conducting, solid and conducting, all the charges will come on the surface. If it is hollow and conducting, again on the surface. If it is thin non-conducting, again, the charges will remain on the, outer surface. If the charges are on the outer surface, we have nothing, no charge available inside, and we have same calculations for all three cases. And if we have a non-conducting sphere, so the charges will be available wherever you give them, right? So it is distributed in a way that you have provided. So we are uniformly charging it, so charges are available uniformly everywhere, right? So like this, okay? So this is the case. Again, apply the same principle that we have applied so many times, right? We have this spherical body, a spherical conductor, which is either a solid conducting sphere or a hollow conducting sphere or a thin non-conducting spherical shell. All three cases are representing same things. All the charges are on the surface with the surface charge density sigma, Q upon A, right? So right now, if you want to know the value of electric field over here at a distance r away from the center, right? So first thing you will do is to know the value of electric field with the help of Gauss's law, right? Assume the closed surface, and the best shape of closed surface right now is going to be another sphere, right? So you have done that, right? And now you need to know the value of enclosed charges, the value of area of the sphere, and then the value of volume of the sphere whenever needed, right? So again, the same things are there, right? You can calculate how much integral of EDA, or what will be the value of EDA and what will be the value of charge. So right now, when all the charges are available on outside, the net charge enclosed with this particular thing is 0. So no electric field will be there inside, same just like cylinder, right? And now if you want to know the value of electric field outside this sphere, so you have assumed a Gaussian surface which is outside, which is passing through the point where you want to calculate it at a distance r away from the center, right? So for this Gaussian surface, again, you have done the same calculations, right? What is that? Calculate the value of phi. What is integral of EDA is the phi, right? So for the entire thing, you see that the electric field vector and area vector, they are parallel. So cos theta is 0, right? So cos 0 is 1. So electric field at every point of this sphere will be constant, right? So it will come out of the integral sign. Integral of dA will be the net area of this Gaussian surface. It has a radius r. Gaussian surface has a radius r, which is passing from this point. So area will be 4 pi r square, right? So the net flux through the sphere will be E into 4 pi r square. I believe the idea is very, very clear. Net flux through the sphere will be E into 4 pi r square, right? Okay, so now let's apply it. Gauss's law, the sphere will be, the flux will be charge inside upon epsilon naught. When the Gaussian surface is outside, all of the charge is enclosed within it. So charge inside is, capital Q, or you can say that in terms of surface charge density, you can say this particular surface has a charge. So this one has 4 pi r square, right? And the surface charge density is sigma. So the total charge inside is 4 pi r square into sigma, right? This is the charge inside. So for the sphere, it is charge inside upon epsilon naught, sigma into 4 pi r square upon epsilon naught. That is your answer, right? Okay, so let's move on and talk about the next part, which is this sphere. We know the value of phi of a sphere, which is E into area, right? So yeah, we have calculated this particular part as well. So charge inside upon epsilon naught, this is the value, right? Okay. And when you solve it, just put those two things next to each other. You know the value of flux, you know the charge inside upon epsilon naught, put the values next to each other and solve it. You will get the value of electric field is changing with the square of distance, right? With the square of distance, right? In the case of cylinder, right, it was, in the case of cylinder, you see what was happening, you see? In the case of cylinder, hollow cylinder, when you go outside, the value of electric field changes with inverse proportionality, right? In the case of cylinder, it changes with inverse proportionality, right? Even if it is a hollow cylinder, it changes with inverse proportionality, right? But in the case of a sphere, right, if it's a hollow sphere, the value of electric field changes with, 1 upon r square, right? It changes with 1 upon r square, as you can say, right? So you see that if you want to plot the graph, it will come out like this. So inside the shell, you have no electric field, and outside it changes like this, right? Inverse square relation, right? So for a cylinder, it changes with inverse relationship, and for a sphere, it changes with inverse square relationship outside, right? Okay. Similarly, you can go for the solid as well. For the solid, you will have a volume charge density rho, right? Again, you will assume a Gaussian surface through passing through the point, place of interest. And if you want to know the value of electric field inside, you will assume a Gaussian surface passing through inside. If you want to know the value of electric field outside, you will assume the Gaussian surface passing through outside, right? So this part I have written in this part, in this particular notes very well. You can go through that and you can easily understand that part, right? Over here I have written, first of all, you can calculate the value of flux, right? Again, theta will be 0, right? So integral of dA will be the total area of the Gaussian surface, right? And right now, this surface is not enclosing 0 charge because it's a non-conducting body, right? So it will enclose some charge. What is that? How much charge will be enclosed by it? We will say that volume of this thing, it is 4 by 3 pi r cube into volumetric charge density, which is rho. So rho into 4 by 3 pi r cube. This is the charge enclosed. Put the value of this thing, and phi you have already calculated, E into 4 pi r square. Just equate them and right? The value of phi, the value of this side, right side, just equate them and you'll get the value of electric field, rho r upon 3 epsilon naught. You see that as long as you are inside the solid not conducting sphere, the value of electric field increases linearly. The same thing was happening in the solid cylinder as well, solid not conducting cylinder as well. solid non-conducting cylinder and solid conducting is sphere. Solid non-conducting is sphere, sorry. They are inside, they have the same variation of electric field. Electric field varies linearly with the distance, right? So, but as soon as you go outside, what will happen? The whole thing will act as a point charge and all of that is inside. So when we calculate it, again, same calculation, exact same calculation, right? When you calculate it, you see that the electric field varies with a square of distance, right? So inside it moves linearly and outside it moves with a square of distance in an inverse square relationship, right? In the case of solid cylinder, solid non-conducting cylinder though, you see that in a case of solid non-conducting cylinder though, when you move outside, right, in the case of solid non-conducting cylinder though, here you have it, here you have it, here, you see that. In the case of solid non-conducting cylinder, you have when the R is more than R, means when you are moving outside the radius of the cylinder. So you see that it changes with inverse proportionality, right? But here in the solid non-conducting sphere, inside it increases linearly, true. But outside it reduces with inverse square relationship, right? This is the main difference, right? So the solid and sphere have a different value, different variation of electric field when you step outside them, right? Outside a cylindrical charge distribution, the electric field seems to varying in a inverse relationship. E is inversely related to R, right? So if you move twice as far, the electric field will be halved. But with a spherical distribution, it changes with inverse square relationship. So if you just double the distance, it becomes 1 upon 2 square, that is 1/4, right? So that's a major difference, right? So yeah. So now let's talk about the next idea. Have a look at this problem. There is a hollow sphere of radius 10 centimeter and electric field 20 centimeter, right? There is a hollow sphere of radius 10 centimeter and electric field at 20 centimeter from the center is E. Okay, hollow sphere is there, right? And it has a radius of 10 centimeter and electric field is given over here at a distance of 20 centimeter from the center and it is saying E. Okay, electric field at distance 5 centimeter from the center will be, because it's a hollow sphere, right? So from there you can say all the charges are available on the surface and no charges inside, and you want to know the value of electric field inside. So you see that it encloses no charge, so there is no electric field inside, right? Okay. And there is a hollow sphere of radius 10, the electric field at 20 is E, find the electric field at the surface, right? So you see that in the case of hollow sphere, right, you know that the value of how the value of electric field varies outside the sphere and outside the cylinder, right? This is the cylinder sphere, right? And the radius of the sphere is 10 and the electric field at 20 is given, right? 20 is given, this is E. Find the value of electric field at the surface. So you see that it's a hollow sphere, so at the surface you will have the electric field, inside you will not have the electric field. But you know that electric field outside varies with this relation, right? Electric field outside varies with this relation. So you see that if here we have E1, here we have electric field E2, right? This distance is R1, right? And this distance is R2. So clearly it is saying that E1 upon E2 is R2 square upon R1 square. Clear? Right, you see that inverse relation is there, right? So R2 square is how much? Or you see that E1 upon E2. What is the value of E1? It is E. The value of electric field over here is E. And the value of electric field over here you don't know. It is E2. Right, R2 square. So R2 is 10. 10 square upon 20 square. So 10 upon 20 whole square, right? So 1 upon 4, right? So E2 is 4 times E. I believe the idea is very, very clear. So over here, when you come to the surface, the value of electric field will be 4 times what you were getting over there, right? And you could have solved it with the common sense as well, but just for the sake of explanation. There is a solid conducting sphere of radius 10 and electric field at the 20 centimeter from the center is E. Find the electric field at 5 centimeter from the center. There is a solid conducting sphere. All the charges are on the surface. Solid conducting sphere of radius 10 centimeter. And the electric field at the 20 centimeter is E. Okay. here is E, all right. So we need to know the electric field at 5 centimeter from the center. So electric field at the 5 centimeter, again it's 0, it's inside, right? So if the net charge enclosed by the Gaussian surface is 0, the net electric flux through the surface will also be 0, right? The flux is net charge upon epsilon naught. So net charge enclosed is 0, then flux is also be 0. Electric flux through a surface is maximum when the angle between the electric field and the normal to the surface is how much, right? So electric flux through a surface is maximum. You know that flux is EDA through any surface, right? So let's try to use a normal basic formula. EA cos theta, right? So to maximize this value, cos theta has to be maximum, right? For given value of electric field and area, right? These magnitudes are fixed. This has to be maximized, right? And to maximize the value of cos theta, theta has to be 0. And for theta has to be 0, we need to have area vector and electric field vector parallel to each other. All right, parallel to each other. So theta has to be 0, by the way. So that is your answer. That is your answer. Option A is correct, right? So that's pretty much everything about the application of Gauss's law. And I believe now the understanding of Gauss's law is clear and the application of Gauss's law is also very, very clear. Now let's move on and talk about the electric dipole and various information and knowledge about the electric dipole we are going to get. Right, let's move on and talk about the electric dipole now. All right, so let us understand the last concept of this video, which is the concept of electric dipole. And in this one, we have these 4 things. First of all, we will talk about the electric dipole and dipole moment. What's the meaning behind that? Then we will talk about electric field due to the dipole, right? And there are 2 situations in it that we need to focus upon. Electric dipole in an external electric field. How does the electric dipole behaves when it is placed in an external electric field? We have seen how does a charge behaves in the external field. Now we need to know about how does the electric dipole behaves in the external field. Then we will talk about the equilibrium of electric dipole. So these are the things we are interested in. So let's start talking about that right away, right? Okay, so here we have it. First of all, this is the structure, right? So electric dipole is 1 unit, right? You don't take 2 separate charges and place it randomly and you call it a dipole. No. You have this thing going on. For example, in chemistry, you know that there are certain particles like HCl molecule you will find, right? You will find HCl molecule, and let's say that there are 2 molecules for that matter. Let's say A and B, okay? And one of them has more affinity towards the electrons. Let's say that they are forming a bond, and you know that. Let's say these are the electrons that they are sharing, right? And they are forming a covalent bond maybe. So what is happening? Let's say that B has more affinity towards the electrons. So it attracts the electron toward itself. They are not completely transferring to the B, right? But they are shifted towards B. So now you see that electron has a negative charge, and if the negative charge is closer to you, you tend to develop the negative charge as well. So B develops partial negative and A develops partial positive. But still this whole thing behaves as a 1 molecule, right? 1 molecule. So there are a lot of different molecules like HCl, right? And all the HCl, HBr and all those things, right? And on top of it, there are other molecules as well, like water, right? Water also has a little bit of polarity in it, just a tiny bit of polarity, but HCl has a huge difference, and so it has a significant polarity in it. So you see that this molecule is 1 molecule, right? It is 1 molecule. It does not, we don't have 2 separate charge particles like that, right? So the dipoles are generally one arrangement where we have 2 charge particles, right? Dipole is considered as one arrangement where we have 2 charge particles separated by some distance from each other, right? So when we talk about the principle of superposition, you remember, right? When we talk about the principle of superposition, we have 2 charges, positive, let's say positive or negative, right? And we want to know the value of electric field over here. We imagine a unit positive charge, right? We say that this is going to push it here, this is going to push it here, and we apply the principle of superposition. And the same thing we'll do like that, right? In this situation, we take the distances from the individual charge particles, right? We need to know this distance and we need to know this distance. So we say that kq by r square, kq by r square. We add them vectorially and we found the net value of electric field. But when we talk about the electric dipole, my dear kids, we don't deal it in that way, right? As I said, electric dipole is a one thing, right? So we don't take the individual distances, right? What do we do instead? We take the distance from the dipole itself, right? Let's say that we have a dipole like this, as a positive charge and a negative charge. This arrangement is an electric dipole. But as I said that mostly what will happen, this is going to behave as a one single unit, and you have to find the distance from the dipole itself, right? So let's say that you want to know the value of electric field over here at point P, okay? So how to know the distance from negative charge or from the positive charge, right? Because we know the distance from the dipole. Point P is at a distance x away from the dipole. So from where this distance x is measured, right? So this is the answer, my dear kids, that if you join the dipole, this is the axis of the dipole, this is the center point of the dipole. All the distances are measured from the center of the dipole. So the distance x is distance from the middle point of the dipole, right? So this is how you understand about this idea. Dipole is considered as one unit, right? And it behaves as a single unit in the external field as well, right? So this is what we are interested in. We have a positive charge and a negative charge placed at a certain distance from each other, right? So what happens, the electric field sets up. So positive charge, emits the electric field line. The electric field lines, we can say, emerge out of the positive charge and they enter or they terminate into the negative charge itself, right? They come out of the positive charge and they terminate at the negative charge. They don't move back. You know that electric field lines are not a closed curve. So this is how the dipole arrangement looks like, a positive and a negative charge. Okay. Now, the distance between them, we can consider that as A as well, right? We can consider the whole distance between the positive and negative charge as L. We can call it length of the dipole, but no. As you know that all the distances are measured from the center of the dipole. So if the point P is here, right, and we are measuring from the center of the dipole and we are calling the whole length as L, so this will be L by 2, right? So knowing this distance will be, whole thing is x and this is L by 2, so it is x minus L by 2, right? And the distance from the positive charge will be, this whole thing is x, this is L by 2, so this is x plus L by 2. So every time this by 2 factor will come up, my dear students, right? We don't want that by 2 factor to come every time and make our life difficult. It is already not very easy, right? So what we do instead, we don't take the distance between the positive and negative charge as L, instead we take it 2L, right? So what is 2L? The distance between the positive and negative charge of the dipole. In some books they are writing 2A. That's the same thing, right? So it has its own benefits. I'll tell you about that, right? So here it is. The dipole moment will come out to be a quantity, right? The dipole moment will come out to be a quantity that represents the value of any one of these two charges, which is Q, into the distance of the dipole, which is 2L, right? Remember that this 2L is the whole thing, the distance between them, right? If they are giving you the distance between the positive and negative charge of the dipole is, let's say, 10 units, right? So know that they are not giving you the value of L, right? L is half of the dipole, the distance between the dipole, right? They are giving you this whole thing, right? So Q into 2L is the value of dipole moment, right? So what's the direction of dipole moment? It's a vector quantity. So from the negative charge towards a positive charge, this is the direction of the electric dipole, right? Okay, and the unit will be Coulomb meter, right? So now you need to know about the magnitude of net dipole moment for this particular thing. So as you know that dipole moment is a vector quantity. Direction is from negative charge to positive charge. So you see that this is a 2Q charge, this is Q and this is Q. So you can imagine that this 2Q charge is made up of two charges. This is minus charge, so you can say it is minus Q and minus Q, right? You see that one of these minus Q charge will make a dipole with this plus Q, and one of the other minus Q charge will make a dipole with the plus Q, right? So we have two dipoles placed in this situation, right? Each of them has a dipole moment from negative to positive. So from this to this and from this to this, right? Like that. So the dipole moment of this thing is here, and the dipole moment of this thing is here. Both of them are perpendicular to each other, and there are two vectors. You need to add them. You need to find the net dipole moment. So it will be a resultant of these two under root this square plus this square. So resultant will be under root p square plus p square, right? What is the value of p? Although we can say the magnitude of one of the dipole moments is q into the distance between them. So q into, here the total distance is given as a. Remember that we are not writing q into 2a here. Why so? Because the 2a is not, 2a was the distance we assumed. Here the distance is given as a. So value of one of the charge into the distance between them, that is the dipole moment. So q into a here is going to be one of the value of p, right? So now you see that once you know the value of p, which is the magnitude of dipole moment, right, it is q into a. So net will be under root p1 square plus p2 square. So under root this square plus this square. So root 2p, which is root 2 qa. So that is the answer behind it. So now look at this particular situation. Here we have the dipole, right, and the dipole creates the electric field, the net electric field, just like any other charge distribution. And now what we want to know, as we have already discussed in the concept of electric flux in the Gauss's law part, that the net flux, electric flux, if you enclose a circle around the whole dipole thing, then the net flux associated will be 0. But not, we are not talking about electric flux here. We are talking about the net electric field, right? So net electric field at any place we can find out by simply doing the same principle of superposition thing, right? You have a charge particle, positive charge particle and a negative charge particle arranged in a dipole fashion, and the length of the dipole we have assumed as 2L. So we have an axis of the dipole and we want to know the net electric field first of all on the axis of the dipole at a point P, right, at a distance x away from the dipole. So clearly the distance from the first, let's say this is positive charge, this is negative charge, the distance from the negative charge will become x and this is L, right? So it is x minus L, right? And the distance from the positive charge will become x plus L, right? So see that negative charge is creating the electric field over here. In which direction? Imagine a unit positive charge. First of all, negative charge is going to attract it, positive charge is going to push it. Since the negative charge is much closer, the attraction would be much larger than the positive charge repulsion of the positive charge, right? So there will be a net electric field moving in this direction. Net electric field will be in this direction, right? The net electric field will be in this direction in this situation, right? So the direction of electric field is from negative to positive. The direction of net electric field is also in this way. So right now you can say that the net field is supporting the net field is in the direction of dipole moment of the dipole here, right? So right now you see that how are you going to deal with this? The net electric field will be E1 plus E2, right? Just add them with a correct sign and you'll get the answer, right? There's no confusion in that particular part. So this is the arrangement, right? And this is the distance from the, this is where we have to find out the value of electric field, right? At an axial point, so the point on the axis, at a distance x from the center of the dipole, right? So here what we are getting, right, here it is E1 and E2. E2, as is understood, that it is the dipole, it's the value of electric field due to the charge particle E2, right? So it is much closer, so it is going to be higher value, right? So right now you'll see that the value of E1, the electric field due to the first charge particle, the distance, overall distance, you know, L plus X, right? So KQ by R square, so KQ by L plus X whole square. Now the whole thing is there, right? We have the other charge particle. The distance of the other charge particle is this much. So the whole thing is x. This is L. So this is x minus L, right? So KQ upon L x minus L square, right? So now the net field will be subtraction of these two things. Net field is because they are in opposite direction over here. Just apply the principle of superposition and subtract them. Take the LCM and solve it. This is the value of net electric field that is coming out, 2 kpx upon x square minus L square to the power 2. Now, if the value, now dipoles, as you have seen, that dipoles in nature are quite small, right? They are on a molecular level generally, right? So if the distance 2L we talk about, this distance, this is going to be very, very small, right? As compared to the value of x, right? So the distance of the length of the dipole is very small as compared to the point where they are, as compared to the distance of point where we are calculating the dipole moment or net electric field due to the dipole. So generally what happens, L is fairly small as compared to x. So for most of the observation, we can ignore the square of a small quantity compared to the square of a large quantity, right? And once we do that, right, since x is much larger than L, so if we do that and if we remove L square from the calculation, so you see that it will be x to the power 4 and there is a x in the numerator, it will cancel out. So in the denominator we will have x to the power 3 left with us, and this is how we will get the value of electric field is 2 kp upon x cube, right? 2 kp upon x cube. So if you have a dipole, then at the distance x from the center of the dipole on the axis, the net electric field is 2 kp upon x cube. I believe the idea is very clear, right? Okay, let's move on and talk about the next idea. Here we are trying to find out the value of electric field due to the dipole on the equatorial plane, right? So this is the equatorial plane, this is negative, this is positive, this is the middle point. The plane passing through the midpoint is the equatorial plane, and you are somewhere on that plane here. So this is the point S. Now the distance, the dipole, the place where we have to find out the value of electric field is at a distance x away from the center of the dipole. This is x, right? Now, when we are going to use the values, so negative, and imagine a positive charge, test charge over here. So negative will attract this thing over here and positive will repel it like this. So the net field will go like this, right? So if you understand with a common sense, we will say that if you take the component of this force and this force, right, you see that the vertical components seem to be cancelling out because the distance is same, right? And the charges, the magnitude of charges involved are same. So the magnitude of forces are also going to be same. So vertical components will cancel out and the net components in the horizontal direction will add up, right? The net component in the horizontal direction will add up. Now you see that the dipole moment is from negative to positive. So P vector is in this way, and the net electric field is coming out opposite to the P vector. So there will be a minus sign in the electric field, right? So let's try to do that. This is the values of, this is the directions of electric field first of all, and here is the theta first of all, you see, right? So now what is happening, right now what is happening, you see that if this is theta, so this is also going to be theta only, right? So the component E cos theta in E sin theta will be there, and similarly for the other one as well, right? So you see that the horizontal component adds up, right, for both the forces, and vertical component, they cancel out, E sin theta and E sin theta. So the net force is in this direction, net electric field is in this direction, which is opposite to the direction of dipole moment vector, right? Okay, so here we have it. E1, E2 is kq by r square, right? So all the values are already given to us, right? What is this? So here you have it. Here you have it, right? Now, when we are going to talk about the value of E1, so it is the value of electric field due to this charge. So it depends on this distance. Now you know the value L, right? Half of the dipole length, it is L. This is x. So this is going to be L square plus x square, right? So the value of electric field is going to be, kq upon r square. This square, so under root will be removed. It will be x square upon L square in the denominator, right? This is the value of E1 over here, kq upon L square plus x square, right? Under root is removed. Similarly, it goes for the E2 as well. The magnitude is going to be the same because the charges are same, and we are finding the value of electric field at the same distance. So E1, E2 will come out to be the same, right? Which is E only. Now, as you said that the net electric field is just the horizontal component, this E cos theta plus E cos theta, which is 2 E cos theta. So this is the value of electric field written over here, right? Now you need to know the value of cos theta, right? Now you need to know the value of cos theta. So you can look into this triangle, right, and put the value of cos theta from here, right? So it is L upon under root L square plus x square. Just put the value over here, right? L upon under root L square plus x square, right? And then put the value of remaining terms from this one and then solve it, right? Just put the value of remaining terms from here and solve it. The value of electric field is this, kq upon x square plus L square. So value of electric field you put over here. Value of cos theta in this triangle I have shown you, right? It is L upon under root L square plus x square. So this is what you have done, right? Just solve it and you'll get this one. And again, as I said, generally the dipole length is fairly small. This L is fairly small. L is half of the dipole length. It's fairly small as compared to the value of x, right? So you can ignore it. A square of L can be ignored as compared to the square of a much larger number x, right? So in that case, if x is very, very large as compared to L, which is generally the case for small dipoles. So this is what you get, right? This is what you're left with. Minus sign is representing something. What does that represent? It represents that the direction of electric field due to the dipole on the equatorial plane is opposite to the direction of P vector, which we have figured out as well. Right, direction of electric field is this way, right? And direction of dipole moment from negative to positive is this way, right? Okay, so it is minus kp upon x cube. This is the answer, right? There it was 2 kp upon x cube. Here it is minus kp upon x cube, right? Now, this was a simple thing, right? You just to find out the value of electric field due to the dipole, which is just two charges, but the way you take the distance from the dipole is different than two individual charges, right? And here you have to find how would a dipole behave in the external field. So as I have told you already, if they were only two charges separated with each other, right, they would behave pretty much independently, right? If the distance is too large, right, and they don't behave as one unit. But the dipole, as I said, it pretty much behaves like a one single unit, right? So if the external field is there, so it tries to behave as a one single unit in the external field. It rotates, it tends to rotate in the external field, right? What is happening? Here you have the external field. External field is from the higher potential to the lower potential. Higher potential you can represent with the positive sign, lower potential you can represent with the negative sign, right? Now you look at that, the positive end will try to go towards the negative end, and negative end will try to move towards the positive end like this. So right, so you have the positive and negative charge of the dipole, and one is experiencing a force this way, the other is experiencing a force this way. So that will try to turn the dipole. That will create a torque on the dipole. So in the external field, dipole experiences a torque. A single charge experiences a force, right? A dipole experiences a torque. So we are interested in calculating the value of the torque experienced by a dipole when it is placed in the external field, right? So this is the dipole over here, right? Just for the quick recall, you can say that there are two masses, right? F1 is experiencing force F this way, the other is experiencing force F this way, and they are connected with a rod. So if one is, and both of them are experiencing two forces, so they will form a couple and it will rotate the whole thing, right? They are connected at the end of the rods, no? So it will rotate the whole thing. So what is the value of the couple that you will create? It is 2 RF sine theta. So this is what you can understand. Similar thing you can talk about in this way. So you have the value of force, right? And about this point you want to know the how much torque will be created. So you know that the perpendicular component of this distance, this is L, this is theta. So perpendicular component of this value will be L sine theta, right? So how much torque will be created? We can say force into the perpendicular distance about the axis of rotation. It is L sine theta. So we have this thing. So the net force, of course, net force on the dipole will be 0. One force is attracting this way, the other force is attracting this way. Net force on the dipole will cancel out. There is no net force, but the net torque is there. How much is the net torque? Torque experienced by the positive charge plus the torque experienced by the negative charge. This is moving in this way, the other is moving in the opposite way. So basically, this is moving this way, this is moving this way. So both of them are trying to add up. Both of them are adding up. Both of them are experiencing the torque in the same way basically. So the net torque will add up, right, like this. So just add the values over here, my dear students. So over here, what will happen? The net torque is going to be the torque experienced by the individual charges of the dipole. So you have seen it. The force experience is QE, and it is L sine theta. So QE into L sine theta is the value of torque experienced by the first one, and the same is experienced by the other one. Just add them up. So it is 2 QE L sine theta. Now, the distance between these two things is 2L, right? Positive and negative charge. This is the length of the dipole. So 2 and L. And the value of one of the charge is Q. So Q into 2L. Q into 2L. That is charge into the distance between the charges, right? The value of charge into the distance between the charges. What does that represent? It represents the value of dipole moment, right? And we have the value of electric field as well. So Q into 2L represents P. P E sine theta, right? So this represents P. It is P E sine theta, right? And if you try to represent in the vector format, because the torque is a vector quantity, so P E sine theta can become P cross E. Why it is not E cross P? Because that's what we have figured out by looking at the direction of torque, right? It is P cross E. So remember that the value of torque itself is a vector quantity. The value of torque is P cross E. So if you have to find the direction, you can put the value, you can put your hand on P and then turn towards E vector, and that's how thumb will point towards the direction of torque. All right. So this is it, right? Now let's talk about this idea. So over here, what is happening? This is torque is P cross E. What will be the maximum value, maximum magnitude? So for the maximum magnitude, just sine theta has to be maximum. Theta should be 90 only, right? So when the dipole is placed perpendicular to the field, in those situations, theta is 90. So the torque becomes maximum in this situation, right? Okay. So yeah. And over here, what is happening? You see that when theta is 0 or 180, when theta is 0 or 180, then what will happen? Then sine 0 is also 0 and sine 180 is also 0. So in that situation, torque will be minimum, right? Okay. Now let's talk about the last point, which is the equilibrium of the dipole. Equilibrium means there should be no tendency to get disturbed, right? When we are talking about the particles that can only experience forces, right? For example, charged particles, individual charged particles. So an individual charged particle will be under equilibrium when it is not experiencing any net force in any random direction. So net force along x should be 0, net force in y should be 0, net force in z should be 0. That's how you talk about the equilibrium of individual charged particles or any point bodies. But here we have, a dipole that can behave as an extended body like this. So it can experience the torque as well. So for any this dipole to be what you can say, for any dipole to be under a stable situation, under the stable equilibrium, just forces being 0, net force being 0 will not be enough, right? So you see that generally for a charged particle, for a single charged particle, if the net force is 0, it is under equilibrium, right? But when we talk about a dipole, net force is 0 anyway. But what else has to be 0? So the other thing is the net torque, right? So you see that there are two possible situations, right? When the dipole gets aligned with the external field in this particular fashion, you see that it is not going to experience any torque. But there are two possible situations. In both situations, it is not experiencing any torque. Theta is 0 and theta is 180, right? So if you look at that, first of all, the direction of electric dipole P vector is negative to positive. So it is in this way, electric field is this way. So here theta is 0, right? Now, no net torque is experienced here. And similarly, when the dipole moment vector is here, electric field is here, it is 180 and no net torque is experienced over here. So in both situations, net force and net torque is 0, right? Net force, this QE and QE cancel out. Here also, this is going to be positive end and this is going to be the negative end, right? From higher potential to lower potential, right? So negative end will get repelled over here and positive end will get repelled over here. So net force is 0 and net torque is also 0, right? So both the situations are representing equilibrium, no net force, no net torque. But one of them is a stable equilibrium, one of them is a unstable equilibrium. How is that? A stable equilibrium is such that when disturbed can achieve itself back, right? You see that? Here, if we try to disturb the dipole from its original place, let's say we disturb it from the original place and we move the dipole over here, it is negative and it is positive, right? So when it is positive, you know that the external field is from higher to lower potential, positive to negative. So this positive end will be attracted toward this side, negative side, and this negative end will be attracted towards the positive side, right? And this will alone rotate it back towards the original place, right? So this will bring back the original place, or it will try to bring back to the original place. So there is a restoring torque acting in this situation, and this restoring torque is a proof that this equilibrium, when the theta is 0, is representing the stable equilibrium because we have a tendency to restore. In the case of, in this particular case, what is happening, my dear students? If we disturb it, so if let's say positive comes over here and the negative comes over here, right? You see that what will happen? Positive and positive will repel and negative will repel, right? So you have slightly disturbed it, now it will get overturned, right? So there is no restoring torque in this situation, right? So this is the difference between the positive stable equilibrium with the which gets restoring torque when disturbed from the stable equilibrium, and here the unstable equilibrium which get overturned when disturbed from the unstable equilibrium, right? Okay, so that's a major difference, right? Okay. Now look at this question. An electric dipole is placed at an angle of 30 degree with the electric field. Intensity 2 × 10 to the power 5 Newton per Coulomb. It experiences a torque equals to 4 Newton meter. The charge on the dipole, if the dipole length is 2 centimeter is. What will be the charge on the dipole? Okay. So simple thing is given, right? Torque is Pe sine theta. The magnitude of torque is Pe sine theta, right? This is the magnitude of torque. All right. So right now, what they are giving us, the value of theta is given, right? 30 degree. Electric dipole is placed at an angle 30 degree with the electric field. So theta is given, right? And the intensity of field is given. So the magnitude of E is also given, 2 × 10 to the power 5. Theta is given 30, right? P, it experiences the torque equal to 4 Newton meter. So the value of torque is given 4. The value of dipole length is given. So the value of dipole moment is charge into dipole length, right? So remember that many times kids do this mistake that they don't use dipole length. They don't use the dipole length as 2L, right? Sometimes they just say Q into 2L in place of L they put it, and they put the value of P as wrong. So here we have 2 centimeter, so it is 10 to the power minus 2, right? So everything is given, just Q we have to find out. We can solve it and figure out the value of Q like this, right? That's it. And now let's move on and talk about the next question. Here we have it. A molecule having the dipole moment P and momentum of inertia I about an axis passing through its center. It's suddenly subjected to a uniform electric field E at right angles to the direction of molecule's dipole moment. Okay. Find the magnitude of initial angular acceleration of the molecule. Initial angular acceleration of the molecule. Okay. Right. So you know that in physics, that force is equals to mass into acceleration, right? Okay, we know that. So let's represent everything in a scalar fashion. Okay. So force is mass into acceleration. This is for the translatory motion. When you push the body, pull the body, you apply the force, then it is mass into acceleration. There are linear motions involved, right? But when the bodies can not just translate, but they can also turn, right? So in that situation, when the turning is involved, so you're not applying force, you're applying torque. The purpose of inertia is replaced by moment of inertia, right? And the linear acceleration is replaced by angular acceleration, right? Okay, so right now we are turning things, and there is a torque also acting in the situation. Torque is I into alpha, right? And over here, another formula we already know, the value of torque, which is Pe, sine theta. So we can use both of them and calculate the value of initial acceleration. So we know that torque is also, the magnitude of torque is also Pe sine theta, right? So all other things are known to us, and we just need to find out the value of alpha. So we can just equate them, these two things, and get the value of alpha, right? So we know the value of torque and this value of torque as well. Just equate them and get the value of alpha, which is Pe upon I, right? So that's pretty much everything, right? That's pretty much everything about the dipole moment, right? Okay. I hope, my dear students, you have understood the concept of electric charges and field, which was the first chapter of grade 12th really well, right? And beyond that, you still have a place where you can go and just practice the problems of this particular chapter, right? We have selected some really good problems for you and provided you in the link that you can find in the description, right? Just go ahead and download that PPT and that particular PDF and solve those questions, right, on the PW app, right? So just go ahead and practice, because that will make you perfect, right? This is pretty much everything about this particular topic from my side, right? I'll see you there in the next video with few more interesting concepts. Till then, take care. Bye-bye.